take you to the laboratories, so they will help you learn how to make different methods. What we are going to do, will they will do the demo, and the part of that you have to show the efficient basically what is available in each department. So today, this is an schedule of this Gian program. So hope we will be make use of the facilities and attend all the lectures without break. So if you have a number, try to close them so that the others come and then we can attend. Thank you. Thank you.
I hope you have a nice afternoon, and I hope you have a nice afternoon, and you take a breakfast today, and you have some power to participate in my lecture. I hope that you not hate me after free lecture today. And no, such lecture is focused on foundation of nonlinear optics. Nonlinear optics is, in my opinion, one of subject which is most explored in India, especially South India, in Tamil Nadu. I would like dedicate my present talk to former director of Crystal Growth Center, Professor Dana Sekaran from Anna University, Chennai, which was for a long time my very good collaborator, friend, and he also showed me a different subject connected with nonlinear optics, is so-called organometallic crystals. It is also Indian specialty. Many groups growing very good quality crystals, and from time to time they obtain a material which not only possesses very good nonlinear optical properties, but also may be introduced to industry, because when you utilizing, for example, pointer which is lighting in green, it is not inside a green laser, but it is infrared laser, which radiation is transformed into different spectral range. And Okay. The lecture schedule will be focused on few points. It is introduction to nonlinear optics and second harmonic generation and methods of creating non-center symmetry, because phenomena of nonlinear optics is strongly conjugated with a symmetry of media. And later I told some example how applied nonlinear optical phenomena to investigate materials properties, investigate and monitoring processes, preparing different kind of materials. And I told about some remarks regarding composition structure and second harmonic generation intensity. And as finally, I told about my and my group, international team, investigation of some nonlinear materials utilizing simple spectroscopic methods. I hope it will be quite interesting, because a story of nonlinear optics is very strange. I thought why. It is a question. Is it possible change color of monochromatic light? It's difficult to do because for example, you can tell, we have color crystals, color grasses, put radiation. It is not good, because we when we utilizing ordinary light, it is sunlight, for example, we utilizing not monochromatic light. But here is a different phenomena. It is a question. And answer, up to 1960, no. But why later? What's happened? In such year was discovered laser. You know what is it, a laser? And laser generating monochromatic light, a coherent light with a very strong intensity. And sometimes many discoveries in physics was discovered not intentional. And here also was a similar situation, because in students' laboratory was performed experiment when people focused by lens ruby laser beam, pass radiation across quartz crystals, and radiation was splitted by prism. And it was a great surprise what happened, because except fundamental radiation, we obtain also radiation with 2 times higher frequency. it was a great surprise. And when authors try to publish article in serious journal, it was a physical review letters, after editor correction, such small dot which present intensity of so-called second harmonic generation was too small, and he considered it as a mistake and removed it. It was a surprise because efficiency as such process is not so big. Only some percent of fundamental radiation change on second harmonic. And such phenomena was interesting because, as you know, history of physics, it was many similar phenomena, like a discovery, for example, high temperature superconductivity. Authors not have idea about superconductivity. They perform ordinary measurements of ceramic utilizing in electric industry. Yes, it is explanation as such information, and a such experiment was discovered in students' laboratory. Sometimes people came to job and play, and as results they obtain very good results of work. And for example, discovery of some recent materials like, for example, graphite. People playing. They came to job in Saturday and Sunday, perform some experiments, except his job, and they utilizing very simple technology, but equipment for application for measurement or detecting was very expensive. It was electron transmission microscope. Okay, what happened when we put a laser beam on a special kind of crystals? Because it's not all crystals generating a second harmonic generation. I thought about it later. When radiation go across crystals, crystals with interaction electromagnetic field with crystals generating a second harmonic. It is a double frequency in compared to fundamental beam. And we have two laser beams with a different frequency, but is also additional remark is important that it is a coherent beam. It is some remarks regarding comparison between optic and nonlinear optic. In traditional optics, some coefficients like refractive index, absorption, are independent of light intensity. The principle of superposition and fundamental tenet of classical optics is holds. The frequency of light cannot be altered by its passage through the medium. Light cannot interact with light. Two beams of light in the same region of linear optical medium can have no effect on each other. It is also important because by light we're not controlling another light. Nonlinear optics. It is a sum difference, refractive index, and consequently speed of light in optical medium change with the light intensity. It is amazing, but it's true. Principle of superposition is violated. Light can alter its frequency as when it is passed through nonlinear optical materials. And last is important, but utilizing light, we can controlling light. It is both phonons interact. But it's important that such interaction is across medium, and such medium is very important in phenomena. And from a mathematical point of view, the nonlinearity is usually a very weak effect, and relation between polarization and electromagnetic field can be dividing from linearity and maybe expand as power which is depend of intensity of electric or magnetic field. And here we have some example what we can do. It's also interesting that taking account a very simple equation, we can confirm that nonlinear effects not exist in central symmetry media, second order. Yes, it is in such equation we see that a second harmonic generation not exist, but also appear effects of higher order. And what is also interesting, that second harmonic generation is an effect of interaction light with medium. And when radiation go across crystals, intensity of the fundamental radiation beam decreasing, but intensity of second harmonic increasing. And we have longer distance. Is interesting that one intensity decreasing, but a second increasing. But it is not. It is for ideal materials, because you know that each materials have absorption. It is connected with absorption, that also not all energy of fundamental is moved into second harmonic. And here you in such a picture you see like looking it, but we have radiation from laser. It is a fundamental beam, and is intensity changing, but appear second harmonic with frequency 2 times higher. It is interesting because it is a principle of conservative energy. Yes, when we generating some phenomena which need energy, energy of generator, the creation. And also is interesting phenomena arise. It is a so-called phase matching, because in materials we have a refractive index which is depend of frequency. And for example, when we split sunlight on prism, we splitting particular frequencies and you see different colors, though non-stable refractive index. And here, what does it mean? What one wave and second broadcasting with different speed. We have two waves with transporting by crystal with different speed. What is what is a result of such? Results of such effect, as we can calculate, is a modulation of radiation, because both waves interact, and we can to see some strange processes. When we have one crystals with, for example, bigger difference between refractive index for both frequencies, we have a modulation of intensity of second harmonic wave, and it is depend between a mismatch between both velocities, and we have some picture of experiment which confirming existing of such phenomena. It is not good for generating second harmonic, but people know some possibilities how obey such disadvantages. What is requirements for crystals as the materials for parametric light generators? And one of them is absence of center of symmetry, and sometimes belonging to some point groups, special groups which give us knowledge that groups are connected with structure without a center of symmetry. It's necessary to have a large value of component of quadratic polarizability tensor. It is also important because some materials is more interesting for generating second harmonic, but another have a weak polarizability, quadratic polarizability, and it is caused that they are not so interesting for generating second harmonic. Yes, some crystals with a so-called Doppler refraction allows to fulfill a phase synchronity condition. And also it is some interesting phenomena. And for example, when we have a laser with a wavelength 1 micrometer, second harmonic generation will be 500 nanometers. When we have a crystals with a band gap with a start, for example, 600 nanometers, it second harmonic not be generated because it is absorption, in range of absorption. Therefore, there is some problems to investigate optical properties of, for example, halcogenide crystals. It is crystals which window transparency very often start from 600, 700 nanometers. And when we, in most laboratories, utilizing some laser with fundamental circa 1 micrometer, it is very difficult. We should buy a more expensive laser with wavelengths or 1 micrometers, 1.5 or 2. Also is important parameters. It is resistance to surface and bulk radiation damage. It is so-called high laser damage threshold. It is an important element because, as you know, intensity of second harmonic generation strongly depend of laser power. And when we put a strong laser radiation on crystals, what processes arise? For example, absorption, because it is no media except vacuum which possesses zero absorption. And part of such energy changing on vibration, and it is so-called heat. And sometimes maybe destroy it or melt crystals. You see phenomena when laser radiation destroying matter. When we have materials with, for example, low coefficient of thermal conductivity, all materials which in useful spectral range possess medium absorption, and part of energy exchanging on crystals, and crystals will be destroyed. It is also important, especially for, as I call, Indian science specialties, organometallic crystal, when a temperature of melting is start from 100 centigrade to 200-300 is depend, but it is great advantages because such crystals possess many advantages like high polybariability, very wide spectrum of transparency, and such phenomenon may be destroying crystals. Also is some advantages when crystals possess some imperfection, because when crystal possess imperfection, also is scattering inside and generating more heat. It is a many phenomena which coexist with nonlinear optics and is mostly difficult to overcome. And I told about such last point. It is high optical quality. And last, when we like transform radiation, we need a quite big size single crystals. I show you that we can perform measurements of nonlinear optical properties material utilizing not single crystals, but for application like transforming when we need, for example, change laser radiation, for example, for medical application and for beauty science, when is necessary to utilizing a special kind of radiation, utilizing special wavelengths to for example, interact with human body when we have illness or imperfection, when we shoot some removing. And we buy one laser and utilizing second harmonic and put shooter, for example, to block fundamental, pass only second harmonic, and utilizing one crystal, we have two lasers. One laser is for micrometer, second for 500. Or when we have a ruby laser, we have UV radiation. It is give us some opportunities, but also bigger crystals give adjust angle of radiation on between surface to fulfill matching refractive index problem. Yes. It is also was for a long time opportunities to collaborate with Indian scientists, because with my and my colleague group, we investigate of or working on founding a method of so-called symmetry break. It is maybe, for example, for axial pressure. When we put axial pressure, we change, for example, crystal structure in one direction. We can utilizing a so-called pooling. We can, for example, put crystal under interaction with electrical magnetic field, and it is broken so-called centrosymmetry, and now I show you some method which we can do. And from such point of view, also is interesting phenomena, because we have a very sophistical tool to detecting or monitoring phase transition. When crystal, during heating, cooling, for example, under pressure, like I told yesterday, over structural phase transition, for example, from centrosymmetry to non-centrosymmetry, we are able to easy monitoring, because when is another structure, second harmonic generation appear when we go from centrosymmetry to non-centrosymmetry structure, and in opposite, when we have a very good signal, second harmonic, and we go across phase transition to centrosymmetric, it is appear. It is very easy because it's a non-contact method. We have a crystals, put a laser beam, and we observe what's happened. When, for example, suddenly disappear second harmonic, it is, we have information the structure changing, or laser broken. Yes. And one of method of broken centrosymmetry is so-called photo-induced second harmonic generation. We use a radiation of additional laser to induce non-centrosymmetry, because when we have a medium after under irradiation of electromagnetic beam, it is interact, and such radiation may be modified electronic centrosymmetry. And here I compare some methods which was utilized for over a problem of centrosymmetry and adopting some materials, some crystals, centrosymmetric crystals, to generating a second harmonic. We can use, for example, acoustic wave. We can put between plates, like in condensator and capacitor, and we can destroying a centrosymmetry. When we put crystals in DC magnetic field or AC magnetic field or electric field, we changing centrosymmetry, because some direction is a privilege. Yes, and here is electric DC field induced, magnetization induced second harmonic generation, and second harmonic generation induced by spin currents, and by crystal size reduction. You remember yesterday afternoon lecture by Professor Abdul Azam. He told that when we have a big piece of material, it has symmetry, but when we go to nano, we change not only electronic properties like band gap, like another, but also we able to influence on symmetry.
Remember some. Can you correlate some live examples market conduct so that we will understand? So this is primarily physics.
Yeah.
So we some from mechanical and other.
Yeah.
So we will, in order to understand easily,
Okay.
some live examples so that we can understand.
Okay, but the next examples will be more convenient for which not focuses on physics side. Yes. Also interesting, but when we investigate some properties of materials, for example, glasses. Glasses is amorphous materials, not should generate a second harmonic, but we can so-called broken centrosymmetry, not permanently during, for example, external field or under radiation, and in such situation we can monitoring some interesting properties of materials, but also, for example, phase transition, because it is strongly influence for behavior of dipole moments, and is from calculation we can understand when we have a phase transition or we have some unexpected behavior, some phenomena which connected with so-called transition in materials, we can monitoring properties of such transition using second harmonic generation. And for example, when we measurement superconductive properties, we can investigate magnetically ordered compounds. Glass transition, it is also important phenomena, and also is important process for monitoring crystallization, because in different application we should obtain, for example, transparent ceramic. We have glass and we like to change glass for glass ceramic. It is a glass ceramic, it is a structure which locally have a crystal structure. And for example, when we utilizing so-called annealing method, because in glass is a special kind of temperature which is called glass transition temperature. And we can describe such temperature utilizing, for example, thermogravimetry. we put a sample to special crucible, and under heating with a special temperature rate, we can see when such temperature is, and is as follow. We put a big sample of glasses in furnace and put radiation. When start crystallization process, we can stop because a second harmonic generation appears. From glass now appears, and we can, for example, monitoring sophistical phenomena in moment when we obtain our needs. Yes, because for example, when we want obtain a transparent ceramics, we not wait to moment when it is untransparent. It will be will be crystallized in higher level. But such give opportunity to see us when a process of decreasing transparency appear. I show just a moment. It is example. And next, I promise to you information, give information how we can monitoring efficiency of generating second harmonic by different crystals. And in 68, it is after 8 of discovery of nonlinear optics, was not discovered, was prepared a method of measurement second harmonic generation properties utilizing powder samples. And it is good information, but also is bad. I told why. Because, as I told, when we have make a lens, or we have utilizing second harmonic generation for as a tool for transformation, laser radiation, we need a single crystals. But in many laboratories, people able to utilizing very simple method grow nanocrystals. And it is, from practical point of view, is less useful. But we can perform measurements and publish paper that our material possesses very good nonlinear properties. But it is almost unuseful. Yes, and but such method is connected with in investigation of nonlinear properties, powders with a different grade, and second harmonic generation is depend of particle size. It is a method where we have a powder, put radiation, and in so-called reflection mode, now in transparent mode, we investigate intensity of second harmonic generation. It is also useful method to compare quality of materials, also useful of materials, because for example, in what is it? For example, here we investigate how efficiency of second harmonic generation depend of composition of crystals, and we perform many measurements, grow a huge number of crystals. In next slides will be it visible, and for example, ternary crystals intensity second harmonic generation is very low in compared to quaternary materials. But also we can apply such method for different materials, but usually method is the same. We have a powder with a different grade and perform SHG measurements in reflected mode. It is a so-called Kurz and Perry method. It will be also continued by in my talk. We also try to predict before synthesis or before start a program crystal grow, whereas such particular crystals possess better nonlinear properties. And here is some results of investigation when we compare the efficiency of second harmonic generation with a band gap of materials. Because we find some correlation, investigate properties several single crystals, which give us opportunity to find a tendency. Yes, when is one of yields of conclusion when the second harmonic generation increase with a decrease the band gap, because when we grow single crystals, we sometimes try to grow a series of crystals with a modification, cationic pair, anionic pair, make a solid solution, but sometimes it's very easy utilizing, for example, quantum chemistry calculation, describe a structure and confirm it is material central symmetry or non-central symmetry, and calculate band gap. Maybe calculation is not advantages of quantum chemistry calculation, but we are able to see a trend. And here give us some information regarding which crystals should be a better nonlinear optical properties. And here is such practical, in practice, experiment was done by Japanese people, which observe a crystallization process. And it was interesting because they have in furnace materials and put and irradiate by laser. When second harmonic generation appears, doesn't mind when a crystallization process starts. It is a very good tool for investigate properties materials during a process of preparation when we have a non-contact method. We put radiation on surface, and for example, when we use laser micrometers, we see nothing. When start to be green, we know that the process of crystallization starts. It is a very good and important tool for monitoring preparation of materials, especially for industry, because now transparent ceramics is a great challenge for science. Here is also very interesting phenomena, because I told why I interested it. Because I investigate strontium titanate. You remember that it is from all lecture in such course. From time to time we talked about strontium titanate is prescribed, yes? Because such material possesses very interesting properties. Because it is over phase transition, and people well know that it is phase transition is circa 105 kelvins. But such materials possess two-step phase transition. In 150, 160 start so-called surface phase transition. That material in bulk is non-centrosymmetric, but in surface, I make mistake. On surface is non-centrosymmetric, but in bulk is centrosymmetric. And such phenomena was investigated utilizing very expensive method. It was a method of neutron scattering. It was necessary to utilizing a synchrotron device to perform such experiment. But I thought how it was possible to do utilizing nonlinear optics, because material start non-centrosymmetric, and people make following experiment. They put in chrysostat samples and irradiate a laser, and when start surface phase transition, materials generate a second harmonic, and we see that surface of samples start green when we use a micrometer laser. But why discover a bulk phase transition? Because we from 150 go to 105 and bulk start non-centrosymmetric. And it is possible make a transmission measurement of second harmonic. When we put radiation, here a second harmonic generation start when is a bulk non-centrosymmetric. And here is results when a second harmonic generation start when temperature start below 105 kelvins, but in surface 150 almost. It was a very useful application because it shows how we can use optical methods to investigate a phase transition. You ask me what is it in my right side, yes? Here. When we discuss about different phenomena, it is necessary to talk about always on non-contact methods of measurement. You know, do a pandemic, we use a special thermometer and not have a contact, not put some thermometers and keep a long time and disinfection, etc. Remote monitoring is a big challenge in nowadays, and we can monitoring, for example, some problems with transmission of electricity utilizing second harmonic generation and another phenomena. But method which I used to investigate the same material was ellipsometry. What is ellipsometry? You know, when we use laser, we can do many experiments. One experiment is investigation, for example, quality of surface utilizing reflection. Yes, when we have not good quality surface, when we put laser beam, it is diffuse reflection. When we have excellent quality, we have a small point on web. It is one method of investigation. I also, when I have crystals and try to check optical quality, I take a crystals, put a pointer, and when it's not diffuse transmission, I hope this crystals is quite good. Yes, it is many method of remotes, but such method which we use, it is more sophisticated when traditional reflection, because it was ellipsometry, not changing only intensity of reflected light, but also changing polarizability, because a polarized light, when reflected on surface, change polarization. And utilizing such information, we can know about materials. For example, we can, in such way, perform measurements of so-called dielectric constant. Dielectric constant spectral dependence. When we have epsilon 1 and epsilon 2, we able to calculate very easy, for example, refractive index. It is very good because it is also interesting for monitoring quality of quantum chemistry calculation, not only band gap, but another parameters we can check. We calculate when such is good, consistent with experiment, such phenomena is well agree with experiment. We can thinking that a new measurement, new not measured phenomena give us opportunity to predict proper results. And here we also utilizing such method to investigate structural phase transition. And here also was interesting because strontium titanate, excellent surface, absorbing from atmosphere many elements, and its surface make not good quality. And it was you should keep in vacuum. But from technical point of view, it is difficult. And I have one project regarding ultra thin films, perovskite ultra thin films for ferroelectric application, and obtain big size samples, high quality of strontium titanate, which was covered several nanometers thin film of different kind of perovskite, and we utilizing phase transition across thin film. We can see inside materials across a field, because such method, spectral ellipsometry, it is very often using, especially in industry laboratories also, give very good results. And it was a surprise for us, because our detected temperature of surface phase transition was detecting almost in theoretical prediction. It was higher. Why? Because such temperature of surface phase transition strongly depend on quality of field. But we have surface excellent, because it was molecular epitaxy was grow substrate, and next was without removing put preventing cover, and we investigate changes of structure across such thin film. It is a very interesting thought. Maybe I make a break, and because it is a time, and after I finish such lecture and start lecture about the solar cells. When we can make a take break, you can drink water, coffee, or Indian tea. Yes? And we meet. Measurements, especially when you like to perform measurements of heterostructure. You know what is a heterostructure? It is a few different layers, and we can, for first, perform thickness of such layers, but a second, properties of each layers during one measurement. It is, and we can do it in sometimes very big spectral range. Here, we perform measurements with a spectral range up to 30 electronvolts. Ordinary spectrometer working in air, it is maybe 5, it is a maximum. When it is in laboratory, when working in vacuum, give opportunity to perform measurements up to 8 electronvolts. It is a very useful tool for performing measurements. It is very, when you buy quite big, quite expensive equipment, it is a Wolam or another well-recognized company, you obtain a software which give opportunity to interpret results of measurements, not include deep in methodology. It is very useful tools for investigate, and I recommend when you have opportunity to utilizing such equipment, not by utilizing your hands personally, by when you know that laboratory of your professor or you, for example, know in internet that, for example, in Delhi, in one institute, they possess equipment. Maybe you can send request. It will be possible to perform such measurements, especially when you like investigate phenomena on, for example, surface of substrate and another interaction as such area when two different films are conjugated. It is very good tool, and as I told, it is mostly for application. Typical application is sufficient as such equipment, but as I'll show you such opportunities or possibilities such equipment is very good. Okay, we go to next step. As you well know, window of transparency oxide materials is not so big. It is maybe 2 and 2.5 micrometers. Yes, and after such spectral range is materials are untransparent. Yes, we have a window where, especially most of oxide based materials possess window transparency from UV up to 2, maximum 2.5 micrometers. But chalcogenide materials possess a window of transparency up to few dozen of micrometers. It is very useful material for particular application. And now I would like told you something, because one of lecture which tutorial which I should deliver yesterday contain information which I would like to use in next lecture is solar cells, and now I try to elongate such as introduction to solar cells, because solar cells material which I discuss special perovskite solar cells is based not on oxide materials but on chalcogenide and halide materials. Okay. And here you have a Mendeleev table and information. What is it? It's electronic absorption age and vibrational absorbing cutoff. And we have a special range. As I told, in optical materials based on oxides is over up to micrometers. And what is it? Where is such materials interesting for us? It is in the same group. Oxygen is a different word, but sulfur, selenium, tellurium is so-called chalcogenide materials. Their behavior is different because sulfur is more dielectric, but tellurium is more metallic. It is a semi-metallic properties, but selenium is between them. And next group is halide materials. It is next column. It is also interesting materials, but when we taking account stability, it is less stability when we go on the right. Yes? And I show you what we can do with such kind of materials in the frame of nonlinear optical properties. And here is, I'm thinking that it will be bigger, bigger screen, but unfortunately it's not so big and not so good resolution. But here is depicted properties of chalcogenide glasses. And chalcogenide glasses is a special kind of glasses without oxygen in chemical composition. And they have also very good properties in red and infrared spectral range because they possess a big transparency window up to several micrometers from circa 0.5 micrometers. And here is information regarding window of transparency of such materials. And generally, for you obtain such presentation is not necessary make photo. I show a window of transparency, and the window of transparency for crystals is more wide. Start transparency fast in compared to glasses, and from such point of view, crystals is more useful for application, for example, in visible spectral range. And next, it is a small introduction to perovskite solar cells. You are able to see some very good materials for nonlinear application. And as you see, they're not environmental safe. You see, thallium is highest toxicity, and in compared to thallium, lead or mercury is environmental friendly. But such materials mostly possess in chemical composition such hazardous elements. It is disadvantages of such materials, except not good resistance against atmosphere. And we can use such chalcogenide materials in nonlinear optics for acousto-optic measurements, optoelectronic, and detectors, because now problems of detectors is crucial from many points of view, also from medical point of view, when we utilizing different kind of radiation to monitoring human body. And here is some classic materials for generation second harmonic in infrared and mid-red spectral range. We are able to see among a different crystal structure and different composition. And in here you see so-called halcohalide materials and materials which only in anionic part possess halcogen. It is also important because among halide materials exist many so-called topological isolators, topological materials. It is also very important for spintronics, but some information about this kind of materials will be also useful for you when you will be reading some scientific papers. And for application to nonlinear optics, especially for generating second harmonic generation, is important to grow single crystals. Single crystals, halcogenide single crystals, is grown by utilizing Bridgman-Stobacher method. It is quite different to grow oxide single crystal when mostly Czochralski method. He born 30 kilometers across a place when I live, but we not meet, never, because time shift. And here I will show you some example of grow single crystals. It is a great problem because obtain defect-free materials is very difficult, but such size of materials give opportunity to cut on different angle such materials to make plates or for example windows, optical windows, to, for example, try to fulfill a match for second harmonic generation. Here also is some nonlinear optical single crystals. Some of them were doped by rare earths, but I told in next lecture what for. Because such materials may be materials for dual purpose. One, as materials for luminescence, because they have luminescence center, and second, for second harmonic generation. It is interesting because such both phenomena is quite different in physical origin, but for application sometimes both opportunities of such materials may be interested, because for example for pressure sensor, for temperature measurement, we utilizing both temperature dependent of second harmonic generation and for example temperature dependent of luminescence. And sometimes is materials such kind give some additional possibilities. And well, why we can use materials, single crystals and nonlinear optics? You know that we have opportunity to monitoring, for example, pollution of atmosphere utilizing optical methods. And it is a construction special equipment which is a LIDAR. Yes, LIDAR is consists from laser which broadcasting radiation and telescope and detector and detecting system. What is advantages and the disadvantages of such technology? It is a few point of view. One is what we like to monitoring. When we like monitoring, for example, powder or solid pollution in atmosphere, we can use well-known and easy to buy laser. It is maybe typical micrometer laser because when we meet such strong energy phonon with small solid samples, it is back scattering will be available, and we don't destroy a sample and such pollution, because it will be possible to register. But for example, when we have gases is molecules. When we use such laser, it is difficult when you try using gun against me and I put newspaper. Yes, it not back to you, patron. Yes, it is a great problem, and we should use a phonon with a small energy. And phonon for small energy, it is a long wave laser. And it's not so big number of strong laser emitting in micrometer spectral range. This one of them is a gas laser CO2. It is a big equipment you see in some picture with some windows. It is a galvanometer. It is not easy to move. It is a special maintenance need because it is not only pure CO2 gas, but it is a mixing of gases, and they sometimes change mutual composition, and is necessary to adjust. It is a big problem, but it is one of most used as such equipment. And it is as we saw. People ask why we use telescope, not, for example, lens to collect data. No, because when we obtain a backscatter and radiation, they have a different wavelengths. And to avoid different collimation of radiation, though a different refractive index, when we use glass, we have some astigmatism. Yes, we use a telescope. It is not easy equipment. Here you have some more detailed information about it, how it working. It is a mirror here and is backscattered radiation collect here, and is one again reflected from mirror and collected for in photodetector. Detecting of infrared radiation is also difficult because we need cooled detectors, and is a minimum liquid nitrogen. And also such detectors contain in chemical composition mercury, cadmium, and another pollutions. Oh, just a moment. But as such, equipment is well-known, tested, and it is in many commercial equipment were done, except far or mid spectral range. Especially for pollution, it is a many system monitoring quality of air, of atmosphere around a town, etc. is yes. But it's a great problem is proper laser beam. And for example, such system was successfully applied to monitoring Etna plume. You remember that some years ago was Etna was evaporate, and in all Europe was a problem with flight and with some air transport, and they utilizing such LIDAR system mostly not to monitoring evaporated gases, but such nanoparticles, because we can monitoring not only where such particles, because when we put impulse and wait and measurement at time when it's back reflected radiation, we can monitoring where is, but also we can monitoring a moving of such pollution. But a great problem is when we try to monitoring gases. And I told you what is a reason when I start working in such topic. Several years ago came to me a colonel of and head of fire officer school, and told I would like be a PhD in technical science. I have idea because we have a great problem when, for example, is a fire of a chemical factory, and we don't know what is using chemicals to prevent or collapse such fire. And we use chemical detectors when it's necessary came in such pollution, and wait sometimes to obtain results. And it is expensive, and such chemicals, it is necessary frequency exchange because it is validity is not so long. And we try to adopt such system. And it was also great challenge to buy a special laser. Now it will be not possible because it is only few companies in world preparing such laser, and most of them is located in Soviet Union. I was here and buy many years ago. Why such laser is necessary? Because what is it when we have a backscattering? Backscattering is connected with a so-called absorption band. And absorption band of particular gases is very close. And it is necessary monitoring not only in one point, but in few. For example, I a little bit educated in chemistry and know that carbon oxide and dioxide is a quite different gases. One is hazardous, second no. And when we make mistake, or we, for example, ammonia or another gases, it will not go. And it's necessary to put in the same time few coherent laser beam with different frequency. And when we have absorption in 1-2 points, we can detect which kind of gases is in atmosphere. I must hurry up a little bit. And also, here in next slide is information about absorption intensity. And you show that when we use even ordinary laser, intensity in such spectral range, it is micrometers, is very small. And we need to monitoring area above 2 micrometers. It is a great problem, but it is also important because in Poland, I think also in India, you have some meaning, for example, coal and another goods, and except and during process of exploring such goods, it is also connected with gases, and it is mostly explosive gases, all hazardous gases, and it is both is dangerous for people which work, and it is necessary to monitoring as such. And for example, when it's a explosion of bomb, we can monitoring what a chemical composition was used. It is a many possible application, and for such it will be necessary to use such equipment. But it's a problem because such equipment should be mobile. But with such traditional system, it is CO2 laser, it is very difficult. And people thinking how obey it. Maybe we can construct a laser which possess, for example, not laser, gas laser, but it is a semiconductor laser. And it is some solution, but it is easy told, very difficult to obtain interesting results. And here is one attempt of find such materials, because it is some halcogenide glasses with abandoned some luminescence center, give opportunity to broadcasting a strong radiation in such spectral range. It is interesting that is difficult to preparing or make such laser. And next, I should show you, it is a little bit problem, because I fastly complete such lecture. And previously I show you why we can predict properties of nonlinear properties utilizing a standard spectroscopic information about materials. So we speak about a band gap. But recently, I little bit working in optical materials for lighting, and with colleagues which specially focused on searching new materials, we found a very interesting phenomena, and have idea how detecting nonlinear properties or predict utilizing, for example, simple spectroscopic materials. A source was as follows: two isostructural materials. One is lithium vanadate, as second lithium phosphorate materials. Almost the same crystal. One is vanadium, is excellent nonlinear optical crystal, but phosphor based material is no show nonlinearity, and it was a surprise. Why? And we check a structure, we're analyzing structure, and thinking here is not a big difference, because such the structure is quite different, or mostly different when famous organic crystals is was as reference material, and it was a problem how it's solved. And there is a problem if we can explain a high second harmonic generation intensity in lithium vanadate, and understand why lithium phosphorate is not nonlinear optical crystals. And here it is a little bit of physics, and because physics is also important, but and I would like explain you why. When we perform a quantum chemistry calculation, modeling electronic structure of such materials, and we modeling so-called density of state, we can see a great difference between both materials. Unfortunately, it's not so colors, but I would like explain. I would like write what is it that in lithium vanadate, the bottom of conducting band have a high density of state. Here, close 10, you can see. Yes? And electrons in valence band are delocalized because it is a great delocalization, because it is orbitals vanadium and oxygen exist. In opposite, in lithium, the bottom of conducting band possess a small amount in compared to vanadate density of state, and here when we look for density of state, top of valence band is localized on the oxygen 2p orbitals. It is a great difference, and question is, why we can detect if material is maybe a good quality nonlinear material or worse. It is effect on difference in density of state and bond covalency. And next, I maybe go fast on such step. We utilizing such microscopic description on accessibility, and it was confirmed that such configuration of electronic structure and density of state favorizate lithium vanadite and show that lithium phosphorate have a bad nonlinear properties. And we can explain, but such method is quite difficult because we, except performing nonlinear measurements, we also should perform a quantum chemistry calculation to solve such problem. And now we confirming and show why utilizing results of spectroscopic studies we can predict good properties for generating second harmonic, or told that some materials is not good. And now I go fast by such measurements because it is necessary to perform some luminescence measurements, calculate some parameters, and also we take account arsenium anion and analyzing a huge group of materials, and finally we show how we can describe ability of nonlinear, high nonlinear properties utilizing a simple luminescence and absorption measurements. And I hope it will be end of such talk. Okay. And as I told, except materials like oxide materials, which are mostly used in practice, also important groups are chalcogenide and halide materials. Not only for detectors, not only as materials for nonlinear optics in red and spectra red, but recently as such halide and chalcogenide materials which possess perovskite or double perovskite structure may be very useful for current generation, electricity generation by so-called solar cells. And perovskite is, as I told, is well-known materials. Every my talk and Professor Abdul Azam also focused on some perovskite materials because except many amazing properties, they possess one advantages. Halide and chalcogenide materials give opportunity to adjusting not only band gap is a crucial parameter for application for solar cells, but also we can managing electronic properties like photoconductivity, like for example changing properties when we go to ultra thin films or dots or even nanoparticles. So changing electronic structure, especially band gap. Also, some advantages of nano materials when is active surface in compared to bulk materials is much higher. This also is one of advantages of such materials, because sometimes we should choose a method of tuning band gap. You remember from yesterday talk when many properties changing band gap, temperature, pressure, chemical composition, stress, strain, and nanosizing. And now I would like focus on such methodology, how improving properties of solar cells. Because I not will be focused on demonstrating a most technical solution, because I am not expert on technology. I would like give you some information how, from fundamental point of view, we can modify such properties of materials into value which will be useful for our application. Unfortunately, I should deliver yesterday lecture with a tutorial, and now I must put some information during today's lecture, but maybe we tomorrow have more time and discuss about. Okay. And from beginning. Okay. And I would like to talk about physics of adjusting properties absorber to achieve more efficiency in solar cells materials, also show what difficulties is necessary to over to obtain a better quality and better efficiency of solar materials, because it is a two-way. One way is like my colleague, which I meet in India, in Vellore. It was a distinguished professor from Kyoto University, which have a transparent on his laboratory towards 50. And he working very hardly, but you know what is it doesn't mind. When he spent 15 hours in laboratory, his collaborators should be able before them and not go out before him. It is not a joke, but he has very good equipment. He utilizing a very sophisticated method. It is a molecular beam epitaxy, and few millimeter square of solid cells is very, very extremely expensive. But it is for science. But it is one way. But a second way in problem of preparing better solar cells is stability, time of life. Because, for example, when you buy cheap shoes and you go 2 times to university and it will be a necessary exchange, it is not good sold money. And also, we not should think development and still improving of so-called silica solar cells, because silica solar cells have a particular field of application, and for example, different kind, perovskite organic solar cells also have a special way of possible application. And sometimes commercialization of solution, it is a very long time. When I came to India in 2009, and my first conference, one professor told, when you came next time, in our train will be air conditioned, because we cover a roof, organic solar cells, and will be have a free electricity, and over old buses and trains will be adopt and have a very cheap assistant. Up to now, not working, maybe in laboratories, and it was 16 years. And you see that some idea from scientific laboratories have a problem to over such difficulties with a macro, and nobody will be use a molecular beam epitaxy for a growing commercial solar cell. Maybe for space application, maybe, because it is not from economic point of view. Okay. I think that it is some interesting here, and understand such schedule of my talk, because we are after first point, and now we can focus on second. How predict and tune absorber properties. And next, we have some discussion regarding advantages and disadvantages of solar materials. And we talked about a possible utilizing simple solution. It is up or down conversion level to enhancing a spectral absorbance of sunlight. It is working, but not good. But many years ago, it was also very hot topics. And it was sometimes I asked authors of article, you have a profit 5%, but absorption is 15%. And when thin film absorbing 15% of radiation, which should go across solar cells and give improving 5, it is results not so good, yes? But now is only few practical application and only few manufacturers of solar cells applied such technology. What is a general idea of working of solar cells? Absorb all sun energy and transform into current. But it is a little bit problem, because you know what is technology or methodology interaction radiation with a body, with a solid state. It is three processes: reflection, yes, absorption, and transmission. And what we should do? Decreasing reflection, decreasing transition, and all should be left, all energy should be collected and changed by solar cells. We know that it is not possible from physical point of view, but we try how to improve such second coefficient. It is absorption. And it is one of methodology is a multi-duction solar cell. We have one solar cell, here absorbing a part of spectrum and exchanging on electricity, but next utilizing remaining. But it is difficult. As I told, people which inform about 40 or more efficiency of solar cells, it is only special production. It is only for application in laboratories. And when I have a lecture regarding tutorial how improving materials properties, I would like explain you such methodology, because it is also interesting but very expensive. You will know processes which it will be good against TIF. Methodology is very simple. We photons creating electron and hole, and is collected in a system and is resulting producing electricity. It's no complicated, but as we told, we should thinking about a top of solar cells. Top of solar cells have two important functions. First is connected with anti-reflection. It should minimalizing reflection. Second, in your climate, only temperature and water is very hazardous for surface of solar cells. In my climate, when temperature is, for example, -15, it is also a great problem. It is also connected, for example, with expansion, thermal expansion coefficient, because junction, it is connected with a different kind of materials with a different coefficient of expansion. It is a problem because some materials not working properly in low temperature, and sometimes it's a snow, and sometimes it's another dangerous phenomena, and it is a mechanical vibration. It's many problems which should be focused on top layer. And next, when you put a black body outside, temperature may be more than 60. Yes? It is not possible. I tried to visit one temple, but it is without shoes, is necessary, but it was not possible because ground temperature was not give opportunity. I think that it is 60 centigrade, it is a minimum. And also temperature excitation. It is also important for solar cells, especially in hot climate. Is necessary to cooling, such to achieve good efficiency of such materials, because we also should remember when information about efficiency of solar cells is often connected that it is a small letters, that it is 25 centigrade. But it is maybe in cold winter in India, yes, 25 centigrade. Yes, okay. And next, what we can do? Here is a solar cell radiation. I put here a small formula why we can exchange wavelengths on electronvolts, because here is also a problem with a sun energy which reach surface of solar cells. You see, it is a yellow, is a theoretical, or maybe when we utilizing a plane and we put a solar cells on plane which fly in 10 kilometers, and maybe better irradiation. But here we have a problem. It is theoretical, because, for example, when we have smog and another pollution and some not clean surface, it is also final or intensity of radiation is low. Yes, but as we see here, typical solar cells utilizing only very narrow spectral range. It is very narrow. And from such point of view, we have opportunity to improve spectral absorption. because energy of sun is from almost on ground, 300 nanometers up to 2.5 micrometers. And it is a great problem because we should adopt our solar cells absorber to absorbing most of such radiation to properly use. Because when we do it, we win, and we improving significantly properties of solar cells. It is a question. We can do tailoring material to our needs. It is possible? Sometimes yes. But it is some advantages and disadvantages. I'll show you how. Because we have, as I told earlier, some possibilities. Here in such graph I take from a review article. It is also open access. You obtain full information. It is easy to pick up. No necessary to obtain a full PDF. It is maybe here. It is a composition engineering. It is a change of composition. I show how is it possible to change properties utilizing such phenomena. Dimensional approaches. We told also when we have opportunity to change size of absorber elements to nano particles, we also have opportunity to tune gap. We also utilizing strain of stress or stress for such purpose, and it is many methods to absorbing materials. What kind of materials we should use? As we told, we should use chalcogenide or halide materials because band gap, in opposite to oxide materials, is low. Yes, because oxide materials possess a band gap above 4 electronovolts, but it was shown that circa 1.5 it will be most convenient. And we have several opportunities how to do it, but also many materials were investigated up to present very detailed. And for example, when we need, for example, obtain a particular composition, we can find in the literature what we should make, for example, solid solution to obtain a required band gap. I also show you how we can use quantum chemistry for help us to grow and fast because we not have many attempts such properties. Yes. Yes. Here is many good advantages for halide and chalcogenide materials because they also composition strongly influence, and we can able to predict how on most important electronic properties, like I told, band gap, refractive index, photoconductivity, etc. Here is some examples from my previous work. We investigate photoconductivity, we investigate some dielectric properties, and also we show how is melting temperature. Melting temperature is important for stability of materials. When it is melting is higher, materials is more stronger. And you see not only how changing with a substitution of cationic or anionic part, how we can managing with a simple way band gap. For example, when we make a solid solution, we have opportunity very precisely adjust band gap. But also it's important here when we exchange composition, here's a few opportunities. For example, here, for example, we exchange in anionic part sulfur for selenium, because such materials also recently take attention of scientists, not only pure halide materials, but more stable alcohol-halide materials. It is important, but also it's important as such parameters. You can see it is a photoconductivity. It is a ratio between conductivity on irradiation, a special formula and special methodology how do it. It is standardized procedure up to so-called dark, because a dark conduction is also photoconductivity is also caused by thermal excitation. And you see what here it is a 5, 2, 3. It is also one parameter is important is band gap, but a second also is opportunity to generate photocurrent. It is also important parameters. And we investigate many materials. Also, we make some solid solution. And here also, we will use later such information. I show you solid solution of halide materials. It is also single crystal, but most important, and will be also take account later when we will be modified pure perovskite, is such information. You should. It is important because interesting for solar cell application structure exists only when is a special composition. Because when we have, for example, less than 20% of indium, or we have more than 90, structure of materials is changing. And for solar cells application, only a special kind of structure in solid solution give interesting results. When we go over stability of interesting structure, we not obtain good results. It is also very important because it is connected with a modular interaction difference of ionic radii of both elements. It is and here is a next proposition when we can also make some materials when we change above here we changing cationic part, yes, because excuse me, here we changing cationic part and also see how it influence on band gap. And from previous picture and such, this is one information. But materials is more sensitive for changing band gap or adjusting when we put attention on anionic part. It is from cationic you see. It is difference is very small between particular crystals. Here we have also information how we can use halcogenide materials, not halide materials, perovskite, for absorber application, as absorbent application, because, for example, we can utilizing such absorb band for and generate photocurrent in wide spectral range. But sometimes it's a problem with growing particular or big high quality thin films in materials. Here I show you also our interest regarding some solar cells materials, because here we show like we very smoothly able to adjusting a band gap, and I show you how we can utilizing such information. You see, we have a formula. How? Because it was confirmed by experiment, but for example, when we need a band gap 2.8, we need such mutual composition. And such calculation, such measurements were done for many materials. Now, when we have a good access to journals, to library, to method for searching information, we can sometimes utilizing machine learning or artificial intelligence to help us. We can find published results, how properties, how composition should be prepared to obtain a particular band gap. It is halcogenide and halide materials are very useful materials for such. And also we can calculate, for example, refractive index. We can calculate another interesting materials properties for also band gap for a different kind. It is first was my papers, and second also is my PhD student calculation. And here also we have opportunity to managing band gap and it is like absorber. It will be very good because band gap is very narrow. When band gap is very narrow, absorbing range is very wide. Yes, and also it's possible to investigate. But also, I told that not only experiment, not only performing a new junction, but also preparing or doing theoretical investigation, we can improve materials. And here also is information how electronic properties, not only band gap, strongly depend of chemical composition. Here you see how change not only photoconductivity, but also so-called photoconductivity coefficient is changed, because not only important is a maximum for photoconductivity, but also is efficiency to generate photocurrent by materials. And we also, like previously, preparing a solid solution, we can also adjusting electronic properties to our yields. Here we have information regarding different attempts to investigate or existing some solar cells. It is organic hybrid because perovskite utilizing in solar cells is with a cation which is mostly organic element, and I show in next slides. And also we can see that one of most important problem which arise in preparation solar cells is thin film deposition. It is a crucial because we have a different kind of material. We have possible diffusion. When, for example, when some electrode diffuse into absorber, it is strongly change properties of materials. Therefore, a method of preparing thin films, I think, as I remember in one slide, I show some advantages or disadvantages of particular method is important. Because, for example, one of method of utilizing nanotechnology for preparing thin films is make, for example, absorber not from bulk material film, but ultra thin films, utilizing a so-called nano effect. And single crystalline, it is, it is utilizing mainly silica. Silica waffle is produced in big sizes, crystals, and is necessary cut for thin plates, but such solar cells possess very good durability, stability, and maybe after 20-25 years should possess not less than 90% of efficiency. It is also important because when people try to apply it, it is most important parameters. But I don't know it is true because when I was in your age, no, I think 2 times older, was a CD plate and for recording information, and now it's very difficult to find such device, but the people told warranty for keeping information is more than 50 years. But now it's difficult to find device to read such information. It is a joke, but it is also important. And such silica waffle grow as single crystals utilizing a Czochralski method. It was a Polish citizen which his life was not very good, but he was a person which earned huge money, patented very much solution. And for example, he some metal solution with small friction. It was used in railways transport, and he obtained a huge money. But his the best discovery was a method of crystal grow, is well known as Czochralski method, and it is method is applied in industry for growing single crystal solar cells. And as I told, organic, people thinking about organic, but it is difficult to apply it. And now is such group, such hybrid solar cells is a most promising material for future, but with combination with a traditional silica junction. I show how. Here I show some information regarding perovskite. Why perovskite materials? Why? Because it's very popular? No, because perovskite have some good perspectives. When we over some troubles, and for example, especially in Europe, we able to remove very bad lead. When I was a children, we have some figures from lead as for play children. Yes, it is some soldiers, some horses, and we play. But now is a very dangerous element. Yes, because as you remember, I show many crystals which we grow and investigate, which contain hazardous materials like, for example, mercury, like thallium, etc., cadmium. But it's a problem how stable is material. When material is stable and not remove elements to atmosphere, to environment, it is okay. Because lead possess very exceptional properties like hyperpolarizity and polarizing properties. They give them some advantages to be element of solar cells. And at one of slide I show what will be when we exchange such materials. And next topics, what is interesting, people try to utilizing such perovskite for industry. It is for industrial scale. It is also very important because when we not able to grow so-called photovoltaic farms, maybe when in your country, for example, is a many place. It is people not live because it's difficult to live, for example, without water, and it is possible to put some farm, yes, photovoltaic. But when, for example, in Taiwan and countries when Korea, when the countries is very small, but human density is very high, it is a problem. And such solution may be attractive. But it is not question how long. Here is a problem. It is a problem in red. We can remove. For example, we can exchange lead by tin. But efficiency, it is almost 2 times worse. And we should choose a balance. Less toxicity or less efficiency. Unfortunately, in Europe we joking that it is choose not belong to us, but to European Parliament. Yes, they have some regulation regarding cucumber size. Yes, it is not joking. Yes, okay. And here, you remember a slide when I show solid solution of some halide materials. When I told that it is a particular concentration of mutual concentration between bromium and indium caused structural changes. And here also is important because you know from physics when some materials possess a so-called indirect and direct gap. For photovoltaic, direct gap materials are more convenient and more useful and more efficient for application in solar cells. It is one advantage. As such, information we can obtain from simple measurements, or when we thinking about material, we can perform quantum chemistry calculation, and we should where is bottom of conducting band and top of valence band, and when is one on another, it is okay. When it's not, we should choose. But we have a composite with 3 elements, and we A, B, X, 3. It is a chemical formula of perovskite, and we can chemically change A, B, or X. And in next slides, I show you what is the effect of such substitution. But also we can back to some restriction about. Yes, because when we have idea to grow a new materials with a new composition. We should, utilizing very short formula, check if final structure for first exists and for second, which structure, crystal structure appear, because for photovoltaics, only from 0.8 up to 1 is convenient for perovskite structure and for possible application as a solar cells absorber. And here I show you some information regarding efficiency, some important properties of solar cell when we adduce the cationic part. Cationic A, we substitute formalidium lead iodine. It is a crushed material, but such formalinium we substitute by cesium. And when we utilizing 15% of cesium, we obtain a highest efficiency. It is a 16.1%. I also include a link to such free open access article. It is a review article when you have opportunity to find such information. I try to not utilizing huge number of papers to give you more convenient find information which was present. And you remember, here is the best 16.1%. And second, when we utilizing as preliminary material methylammonium lead iodine, we also obtain some information, but here small amount of cobaltium, yes, when we exchange cobalt for lead, we obtain some interesting increasing. Not so big, but it is necessary to understand why 1.6% of cobaltium improving significant, not significantly, but it is 1 or more percent efficiency. I probably think that it is connected with introduced some so-called some changes in electronic structure, and maybe by introducing a defect. Some defect give us opportunity to also improve properties of materials. And also another opportunity to exchange some cationic part, B side, when we exchange some ion of lead by strontium. It is interesting because it is nozovalent material, and also we can see what is efficiency. Efficiency is not so good in compared to previous, but composition is more complicated. Next, we have some, it is a small letters, I'm sorry, but efficiency of such metallo-organic absorber also is not so good. Here is some of iodine we substitute by bromium, and efficiency decreasing. And why I show you? Because it is important to show you that not all our attempts give a positive result. Sometimes negative results may be also interesting, but from fundamental point of view, but from practical point of view, no. But such materials which possess organic part is difficult to calculate, and it's necessary to perform a much of experimental work. And here also are depicted some electronic properties, because a band gap is one element, but also it's interesting to see how introduced changes in chemical composition, influence of absorbance, and performance of solar cell junction. It is also interesting because it is significant significant change due a small change of composition. Here also is interesting situation, but we have a double changing, because we have a change of a cationic part and anionic. Yes, here is the same cation, but composition of anion, especially iodine, is and bromium is changing. It is also influence of absorption, because absorption range changing, but fortunately not strongly influence on best performance. And next is a tune properties by utilizing pressure. Unfortunately, my lecture, which explain possibilities how keep effects like hydrostatic pressure utilizing chemical interaction, will be tomorrow. But I try to show how we can do. It is a similar equipment like we discussed yesterday, and it was perform measurements of structure of materials. As you remember, not only optical properties may be monitoring utilizing anvil cells, but also we can perform structure measurements utilizing XRD radiation. And also you can see how electrical resistance changing under pressure. It is one of method of changing or adjusting properties of material for solar cells utilizing pressure. And here is also opportunity to bandgap tuning utilizing nanotechnology. When we put, for example, ultra-thin film, even solid absorber, we also have some advantages how improving properties. But here only interesting in compared to previous investigation is tiered results when it is a small amount of bromium, when total efficiency of such perovskite solar cells was below 15. And here is a summary of possibilities of tuning bandgap when we are able to move bandgap, taking account different technology, but here is mostly focused on adjusting chemical composition. It is most easy to apply to such method because not need complicated equipment. Here is some solution. It is here is it is a cross section of heterostructure. It is now we have opportunity to perform such measurements and do some technologies, and is sometimes too easy how structure of and microstructure of particular layers also can influence on efficiency of solar cells. It is a technical information, but also next, nanoparticles in solar cells. When we accept a solid absorber, we can use nanoparticles. Here is not perovskite, it is a silica particles. We can also improve properties, absorbance, and efficiency of materials. Here is many attempts how do it, because it is a different geometries, different size of nanoparticles, different shape of nanoparticles. I also give a link to such articles when such attempt to improving materials absorbing materials properties is also interesting. They also utilizing some nanoparticles to cover the surface of solar cells to decreasing significantly reflection coefficient. It is also important for absorbing sun energy. And in the last topic, I'm sorry, last topic is connected with up conversion and dump conversion for application to solar cells. As I told, we should utilizing lost spectrum of sun energy, especially utilizing such high energy spectrum and long but less energetically strong energy from red and infrared spectral range. Here we can use down conversion when UV photon we exchange on, for example, circa red, and also down conversion when we able to reach spectral range up to 1 micrometer, 600 nanometers, to back in a region which is absorbed by silica. And here is also interesting file, a picture which show how much energy we can obtain when we have ideal up and down conversion. It is from a theoretical point of view is quite big because it is such red and yellow. But it is theoretical. From practical point of view, is not so good. But also is I found a very nice solution because I like a nice solution in physics, in mathematics. It is very good when, for example, upconversion level is here because it is light radiation go across, and such remaining is a pass for junction is transformed by upconversion level. Here is a typical reflection medium. But also is interesting that when he have a porous structure, it is give better results when is flat surface interface between upconversion layer and absorbing media. It is interesting because we, for example, not discuss during what is it? Analyzing efficiency of solar cells, how much energy is diffused or broadcasting by some internal reflection, because you know that in interface between two materials with a different refraction index, we always have opportunity to reflect. It is also good when engineers which constructing such system remember about also elements which may be decreasing situation. And only a few slides and will be multi-junction cells. Maybe I'm sorry. I back only one because it will be good. And for example, when we have here not utilized but such junction radiation, we can put here next, which will be focused to absorbing radiation which is not absorbing by such element. And we can do, for example, three. One for UV, silica, and third for infrared spectral range. But it is difficult to do some technical problems because idea is very good, but some reflection, absorption, do some, for example, electrodes, etc., maybe also decreasing results. But such and idea is very very simple. We have one junction, they absorbing some radiation, and for example here is maybe red, maybe, and it is mid-red radiation is absorbing by second, and we have utilized more energy for converting into electricity. Here is also example of some junction, two junction solar cells, and it was interested that they have opportunity to absorbing radiation in spectral range above 1 micrometers. And in right side you see also tandem. It is multifunction solar cells which is connected from perovskite and carbon, silica solar cells. It is also interesting. In my presentation also you find some information of different application of effects of perovskite connected with interaction with radiation, and also some information regarding applicability of particular method on thin film grow, because sometimes it's necessary to utilizing a different method to grow particular layers. It is a very difficult problem, and it is increasing expenses for preparing solar cells, and is called back time, back for money is very long. And here also we have some detailed and fresh, because yesterday I picked up actualized information regarding challenge in best cell production. It is in laboratories up to 40%, but I think that in practice below 30 is know its application. And here is also information regarding a kind of solar cells and how during last several years has been improved efficiency. And last slide is also show how perovskite materials possess efficiency of generating electricity. And here, when you remember that the first perovskite have efficiency 2-3%, now is 26%, but the money for science was perfectly used. But I still wait for such train in cover roof by organic cells and free energy for cooling. It was last slide for that session. Thank you, and I'm sorry for elongation. Thank you for your attention. Electric structural crystal structure, it is possible. And you're able to influence on properties using different kinds of salt. It's also for piezoelectric materials. It is perovskite is very simple materials, very long, but some achievements in, for example, in synthesis, in structure description, and improving of preparation technology, they obtain a new life. And it is perovskite, as you see, it is a typical multifunction materials. It possesses a huge different application among superconductivity, and it is amazing materials, but also many different structure may be using and should be investigate for improve our life quality. Yes, it is amazing when people are able to conjugate a big organic structure into perovskite structure. I think it was one of the best achievements in, I don't know, chemistry, material engineering, I don't know. And you have a question.
So in your last slide, you have shared one graph, pictorial graph, regarding the perovskite and tandem solar cell.
Yes.
It's about 33%. What's about the shock liquid is the limit of this?
Yes, and yes, shock limit can be over when we make a tandem elements because it is some limitation regarding simple solar cells, because most such prediction regarding limitation, it was connected with a simple mechanism. But when we afraid, for example, improving internal reflection, and we make some specific interface between materials, we can over, but it is not from physical point of view, but it is from improving technology. And also, when we have tandem cell, all of them not over limit, but together give interesting results. It is interesting because most of models not include a real behavior of materials. It may be idealized because we not take account all parameters. Yes, and when you, for example, calculate the frequency of balance, you take account that it is angle is very small. Yes, and it's many solution show, for example, utilizing simplified model, and in practice we can sometimes battle. We're not able over speed of light, but some theoretical prediction should be changed because maybe we not take account all required parameters. With some lost do a problem with a solving equation, etc.
What's special about this perovskite regarding to this limit? Does this kind of cell can overcome the limitation?
I think maybe no, but as I thought, when a special solution may be help, because but it is a very sophisticated technology of preparing materials, and it is, for example, molecular strength between materials. We can improve some technical improvements which give us opportunity to improve such properties. But a second question is connected with economical sense, because one is science, one is a laboratory, one is a special application, for example, in space. Or in military application, when we not take account economy, we need only properties, and for such special application, is difficult to find a money except government money. Yes, because for example, when you have opportunity to produce cheap solar cells with efficiency, I think 35, Samsung give you, or another manufacturer give you a huge money. But when you told I have a 50%, but it will be $2 million per square centimeter of solar cells, it will be maybe interesting. Maybe a space agency maybe give you, because maybe they interested. Because special material science is strongly connected with economy. It is huge money is from such sources, and I think that we should wait for next big progress, because I think that we are close a limit when maybe somebody discover new phenomena and new materials, because it is sometimes maybe not intentional. Investigate some different properties. Okay, thank you. Oh, I will be unplugged.
So I'll divide my talk into two parts. So today I will try to explain the first part, and then tomorrow or day after tomorrow, I'll try to take the second half. So after the completion of this particular lecture, so our students will take you to our department, where you will try to, they'll try to give the demo about the preparation of nanomaterials with two different methods, and then we'll try to show you, as I mentioned earlier in the morning session, we'll try to show you the field emission scanning electron microscope. Right, we'll try to give the demo of FESCM. So that completes the today's session. And tomorrow, as usual, you know the schedule. So in the morning session, Professor Michael will deliver 3 lectures, and then he will have the tutorial in the afternoon. Actually, thought of taking today, but from the morning, right, 9:30 to 1:30, he had 4 lectures, right? So we have to respect his age also, right? So that's why I force him to take rest, right? He will continue tomorrow, right? So I will try to share my experience, what we are doing for last 20 plus years. So we are working on the glasses, the amorphous material. Similarly, you are working on the crystalline material for different types of application. Like we have started with the glasses for photoluminescence properties, glasses and glass ceramics for the biomedical application, especially the tissue engineering application, and then the other part, what I mentioned here about the crystalline material. So we are working on the crystalline material also, basically for the photoluminescence application, the nanopass parts, and then the second is related to the tissue engineering application, and then followed by the drug delivery, bioimaging, and then we are working simultaneously on the energy storage. What I'm talking about, the supercapacitors also we are working, and then recently we have started even the photocatalysis application. We are using this material for wastewater treatment. That's why I kept the title as fabrication of amorphous and the crystalline materials for multifunctional application, which suits to our title of the Gian program. So in this talk, I won't go much about the photoluminescence application of the glasses. I will try to stress more on the biomedical application, right? Before going to discuss about the biomedical application, what are the material we are going to use? If you want to use a material as a biomaterial, what are the attributes, right? I will try to explain the fundamentals first, and then I will try to share the research findings, what our scholars are doing for last decade, 1 decade. So I have the results with respect to both amorphous as well as the crystalline material. Now, if you want to use any material as a biomaterial, so if you start from top to, and if you end at the bottom, right, you can find different tissues in the human body, right? we'll have the hard tissues, we have the soft tissues, right? We have the hard tissues like bone, the teeth, and then soft tissues related to the eye, related to the ear, right? And so many other parts are there in the human body, right? So we can able to use partly or completely can replace it, or we can able to use as a filling material. We can able to develop the synthetic organs by means of using this material. So if you want to use any material as a biomaterial, it should possess some attributes, right? It should have the biocompatibility, it should have the cytocompatibility, it should have some sort of mechanical properties also, because you are going to deal with soft tissues, you are going to deal with hard tissues. For example, you take bone, right? So if you want to replace any part of the bone or completely or partially, right? So the metal should have some, not only the biocompatibility, cytocompatibility, it should have the mechanical properties. Because if you take this bone, this bone, this bone or this bone, it is a part of the body and it will try to carry the entire weight, right? So I may have 50 kg, 60 kg, 7 kg, right? Your bone should have the capability of carrying that particular weight. So that's why we are going to concentrate on the mechanical properties like the mechanical strength, hardness, comparative strength, flexural strength, ductility, and so on and so forth. So which is very much essential to develop the hard tissues, right? This is regarding the mechanical properties. And then the machinability is also very, very important. You want to extrude it and you want to mold it and into different shapes. So the manufacturability, machinability, these are all the other properties along with the biological studies. And similarly, we are going to measure some of the physical properties which I am going to discuss one by one, right? So whatever, it's not like you are keeping a book in a rack, right? So it is a material you are going to keep inside the human body, right? So your physiological system should accept your material, right? So if the material is toxic and you are keeping or using as a biomaterial, then it may harm your organ. As a result, the patient may die. So the toxicity is also very, very important, right? Then similarly, there are certain properties you are going to study as far as the metal is concerned, right? So it has to be inert material, or it has to be a bioactive material, or it has to be bioresorbable material, or so there are different classification, right? Different categories of material are there which you are going to discuss one by one, right? So first of all, the material, whether it may be in the form of powder or rod or in terms of a wire or a sheet, right? The body should accept physiologically, and it should interact with the body, and it should resorb, and it should help the body part to grow. So these are 4 generations: first generation, second generation, third generation. So it is not new. So the biomaterial, they are started 50 years, 60 years, 70 years ago, and then there are a lot of developments. So if you see the first generation, the material are known as inert material. So there won't be any activity which is taking place between the metal and the tissue, just like mechanical interlocking. That's the first generation. Second generation is the activity is going to happen between the material and the physiological system, right? So there will be reaction, and then the material will try to participate in the reaction and help the tissue to grow, right? That is the second generation. The third generation, what people are talking about, is the resorbable material. So the material you are going to use as an implant, right? It will be resorbed by the tissue, and it helps the tissue to grow. And similarly, nowadays people are talking about 3D printing with respect to the organs, right? That is also the present generation of biomaterial. So here there are wide variety of materials are available. So people have started with metals and their alloys like chromium, zirconium, chromium, molybdenum, right? So all these metals, they are exclusively they are working for the hard tissue applications, right? Like the bones, the skull, right? So these are related to the metallic implants. And later people have observed some difficulties with respect to these material because they are heavy weight. The metals, if you use as implant, right? So you know that metal is heavy weight. The first thing. Second thing is that there is a possibility of corrosion. If you use a metallic implant in in a body, right? So it has to be there for few years. You won't replace every day, you won't replace every week. What you are going to do, you are going to implant the material and you'll keep it for few years. During the course of reaction, there's a possibility of what you call the corrosion. As a result, what happened, the tissue will try to damage. That is also difficulty, right? So like there are certain disadvantages with respect to the metallic implant. That's why people are more interest towards the ceramics than the polymers, because polymers are the lightweight material, right? And there are some degradable material, there are toxic material. So that is also one of the the problem people are facing with polymers also. Later they are interested towards the composite materials, right? So composite, as I mentioned in the last class also, right? So composite will have two parts, one is the matrix, other one is the reinforced material. So matrix can be metal, matrix can be ceramic, matrix can be carbon, matrix can be glass, and into which you are going to reinforce any material. It is in the form of a powder, can be in the form of fiber, right, in the form of a sheet. So we are going to have different category of composites: PMC, polymer matrix composite; MMC, metallic matrix composite; then CMC, ceramic metallic composite, or carbon matrix, or nowadays people are talking about the hybrid material. So I am not going to discuss about the other properties, other applications of composite. So here I am going to concentrate more on the biological aspect rather than the other, the mechanical application. Usually the mechanical people, they are going to use in the automotive industry, and then even for the defense application. So that is not my area of discussion. My area of discussion is related to the biological aspect, right? So here so these are some of the biomaterials. So you can see here, so there are these are different generation. So when you started our research journey in biomaterial, it was 4 categories, 4 generation. Now it was reduced, it made into 3, right? The first generation implants, you can see most of them the metallic implants, right? And then the second generation is the bioactive and then bioresorbable. We are working in the second generation, and then even we have started to work even in the third generation also, right? But it will try to take some time, right? Here you can try to see the ceramics scaffold, the microspheres, then the fiber, the scaffolds. So this is the latest material which people are working, and this so this already explained to you, right? So a part of the body which has lost the function, you can replace it, or you can able to replace completely, or you can able to correct the abnormalities in the spinal cord. That is also happened by means of the biomaterial. And then for example, you take the pacemaker or the stent, which will try to improve the function of the heart, right? And similarly, you can able to assist the healing procedure, right? So for example, you take the structural, pharmaceutical, you know about the sutures, right? Once the operation is performed, right, after cutting, right, they will try to stitch with the thread, right? So that is also one type of biomaterial. People are using the polymer based material, right? So that comes under the category of sutures. See, we know about the capsule, right? So which will have the medicine inside, the powder inside. So that capsule is also made up of a polymer which carry the medicine into the human body. That is also help the it will try to assist the healing of the tissue, right? So as I mentioned earlier, right, so it is reliable, economic, and then the first and foremost the important thing that we should physiologically accepted by the tissue. Otherwise, what happens, you cannot use it, right? It may be metal, it may be ceramic or polymer or composite, what it may be. The tissue should accept physiologically, then only you can able to use as an implant into the human body, right? So it can be natural, it can be synthetic, right? So it treats, replace, or it assists healing. It will try to improve the function of the body, right? So these are the different organs, and these are the examples of the material which you are going to use. For example, you take the artificial valve, artificial heart, and then the pacemaker. So these are some of the synthetic, grown material. So usually this artificial valve, people are use ceramics, the DRDO. They use the artificial, valves. They use ceramic material to develop those artificial valves. And if you see the second one, the contact lens, the intraocular lenses, people are using glasses, and then even the polymer, the plastics, either the ocular lens or the contact lens, right? And then regarding the ear, so these are the soft tissues. So if you see this ear, so these are the cochlear implant, right? The nose, the soft nose in the ear. So those comes under the category of soft, tissues. So most of the time people are using the polymers and then composite to develop the soft tissues related to ear and then eye. And the fourth one is bone. As I mentioned earlier, this is hard tissue in the entire human body, right? You can start from the top, the skull, to the bottom, right? The bones, right? So the hip joints, the spinal cord. So all comes under this hard tissue. Similarly, having the muscles also, the artificial muscles also people are developing, the artificial skin also, the synthetic skin also, a lot of people are working. So these are the examples. And as I mentioned earlier, so if you want to use any material as a biomaterial, you should have these attributes, right? First one is the biocompatibility. So it should be non-cancerogenic. It should not lead for the cancer, right? It should not be non-pyrogenic, non-toxic, non-allergic. It should be compatible with blood, because you are going to implant this particular material as implant into the human body. And then the sterilizability, and then the physical property just now I mentioned, right? As far as the hard tissue is concerned. And then we have the other one, the moldable, extrudable. It depends, right, what of the tissue are going to develop, right? So as I mentioned, there are wide variety like metals, ceramics, polymers, and then the composites also. So this is regarding the synthetic biomaterial. So polymers we can able to use for the ocular implants related to eye. Then we can able to use to develop the synthetic, the skin, right? And then we can able to use as a drug delivery. The example is the capsule, right, which is to carry the medicine into the human body, right? And then the metallic implants, right? So we can use the screws fix as far as the bones are concerned, and similarly the dental implants, right? If you have visited a dentist, right? They used to have the caps. They used to have the filling material, right? So and they have used pure ceramic, right? And if you are rich enough, you can have gold teeth also, right? It depends on how much you are can able to afford, right? You can have the implants, and almost all the similar properties you are going to achieve with respect to the ceramics. The problem with the metals is corrosion and the heavy weight. So that's why people are more interested towards the ceramics. They are not corrode. They are lightweight, but we can able to achieve the properties similar to that of your metals. That's why it is expensive, but it is advantage compared to the metals. And the other category of metal is the composites. Even people are using semiconductor materials also to develop the implant microelectrodes. Even they are using as a sensors also, right? So these are some of the examples I mentioned. These are the advantages. These are, you can see here. So in metals you are having titanium and it alloys, cobalt, chromium you are having and their alloys, then the gold, silver, stainless steel. So all these material, zirconium is already there. So tantalum, titanium, so many alloys, different combination of alloys you are using, right? Basing upon the compatibility of the material. Similarly, you can see the ceramics also, and you can see the composites some of the examples of composites, and then polymers. So this is the human body, right, from top to bottom, right, where you can able to find soft tissues, hard tissues, right, ocular lenses, uh, the cranial, and then the ear related implants, dental related implants, the blood vessels, right. So the ligaments, the bone fixations. So they are given wide variety of material. This is the old picture, the old image, but now if you search in the net, you can find, still more, material, right? Not this, right? You will try to find semiconductors. You can find different types of, sensor material also, along with these hard and soft tissues. But only important thing is we need to check the toxicity of the material, whether the material is toxic or not, allergenic or not, pyrogenic or not, cancerogenic or not. This is related to the biology, right? So we have a collaboration with the University of Hyderabad and then the other institutes where they are having the biological, the cell cultures studies, facilities. So in collaboration with that only we are trying to do, and then we are having collaboration with mechanical department also, because this is not exclusively related to physics. This is a interdisciplinary area where the biology, the biotechnology, mechanical, physics, and all, the areas, you need to work out. So that's why, we are trying to get some good results. So these are some of the implants, the replacements, right? We can find most of them are the metals, and that is the X-ray, right? After putting the implant, right? You can see the metal, the ceramic, and then the plastic liner. All three you can able to see here, and then the metal stem you can see here, and the ceramic ball you can see there. So these are related to the soft tissues, hard tissues, the bone, and this is related to dental, right? The cap, filling material, or you know about the root canal treatment also, right? So we can able to use even filling material also we can able to use, and the entire teeth we can able to replace with complete pure ceramic metal, or on a metal people used to coat some ceramic. It depends upon how much you can able to spend or how much you can able to afford, right? So these are different generation of you can see the first generation. You can see the different structure, different shapes of the bioactive or resorbable material. They will be in the form of cylinder, pellet, rod, and the third generation you can able to see the mesoporous material, the template, right? We can able to develop by means of the 3D printing. But there are certain practical difficulties. If you overcome the practical difficulties, you can able to produce more implants. So this is regarding the activity. I don't want to go in detail, but so this is the protocol usually people used to follow. I'm talking about the people who are working in the area of biomaterials. This is the protocol they used to follow, and these are the tests they are going to do. Now the first one, what you are doing is the first one. So selection of the material, composition selection, making the metal either amorphous metal or the crystalline material, right? So am I audible? Last. So whether you are making glass, a glass ceramic, or nanomaterial or crystalline material, right? So you need to adopt the technique. If it is a glass, you need to make use of the melt quenching technique, or sol gel technique also you can able to use. If you want crystalline metal, you can able to use solid state reaction, you can use sol gel, you can able to use hydrothermal, you can use co-precipitation. So many methods are there. So first you need to prepare the material, right? And then you need to do the characterization, right? So you made a material. So anybody ready to make use of the material and make it as an implant and allow us to put as an implant in the human body? I made a material. Will you allow me to put into body? Right. So we should have an environment similar to that of the human body, right? So which is nothing but SBF, the stimulated body fluid. It resembles the plasma, the blood plasma, right? So you know, you have the blood plasma. There is, the composition, and there is a protocol to make that SBF. I'll try to show later. So SBF is similar to the blood plasma, right? So we are going to test the material initially with the blood plasma, so which is known as in vitro studies, means outside the human body. So first we need to test whether the material is active or not. So how you are going to test? Who is going to test? You are not ready to test. You are not, sacrifice, right? So I need to create an environment similar to that of human body, then I need to test it. So you are going to test it, but how you are going to confirm whether your material is active or not? So for that, we are going to do some characterization studies. What we physics or material scientists will try to do. We are going to confirm by means of XRD, by FTR, by FPSCM, by ICP, right? There are so many wide variety of techniques are there. By means of that, you are going to test whether the material is active or not. That is the first thing, right? Next one is after developing the material, you are going to do the mechanical properties also, right? Then, so in vitro is over, but we need to check whether the material is toxic or not, because even if you find material is active, still you are not ready to accept my material because you are worried whether it is toxic or not. Then what you are going to do? We are going to take the help of the biotechnology or biochemistry or microbiology. I'm talking about the biomedical area people. People are working in the biosciences. We are to take the help of those guys because they will have the cell culture studies. In cell culture, we are going to do all those studies which I mentioned: cancerogenic, whether the material is toxic or not, whether the material is allergic or not. So all these tests you are going to perform, right? So if you want to test whether the material is toxic or not, right? So we need to extract the salines from the human body. So what we are going to do? We are going to procure. We are not going to extract the salines from the human body. Nobody will have. We are going to procure, right, the salines, right? Bovine salines you are going to take. Bone salines you are going to take. The sarcoma salines you are going to extract. We are going to feed those salines to the material, and you are going to leave like that for 24 hours and for 48 hours, and you are going to see how many cells are live, how many cells are dead. According to the ISO standard, if the cell viability is above 70%, it's about 100 cells you are feed, right? After 24 or 48 hours, if 70 or 80 are remaining, alive, then you can say that the material is non-toxic in nature. After 48 hours, if you observe that there are only 20 cells, means the material is toxic, you cannot use, you have to throw it. So that test you are going to do it. So it is the cytocompatibility study or cytotoxicity study. Similarly, you are going to check whether the material is allergic or not, because that is also very important. So there are so many types of antimicrobials are there. So there are 50 to 60 are there. We are going to test what basing upon the availability, right? Like E. coli, SRS. With the help of that, we are going to check whether the material is allergic or not. Similarly, you are going to check the pyrogenic, other tests you are going to do it. So once you confirm after performing these two, if you confirm that the material is active, bioactive, and then material is non-toxic, non-cancerogenic, non-allergic, right? If you confirm these things, right? So that is our part. But people are not ready because we cannot, take the implant into the body directly. We have to go for the step 3. Step 3 is very, very important. For last 14 years, I'm trying for this, right? So we are, still we'll try. We didn't get it. Maybe in my future. So we have started with Rajkumar, the first student. Even our Sushita also we are trying, but till now we didn't get because it is very difficult. We need to spend 1.5 lakh rupee for particular sample to test the sample. I'm talking about the cost because this is the rabbit modeling, the mouse modeling. Right? They used to develop, right, this type of a laboratory there. They are having the mouse, so not the mouse which you used to find in your home, right? It's a separate laboratory. So maintenance is very, very important, right? So they will try to cut the part where you need to replace it. Suppose you want to use your material as a, I mean, what you call the heart tissue, for example, bone. Which part of the bone you want to replace it? So we need to approach the orthopedician, right? We need to approach the anesthesia guy, right? And we need to approach this, right? And if everybody agrees, then we need to cut and then replace our material, and then you need to check it out after 24 hours, 48 hours, or 1 week. Then we need to check it out with doing some characteristic studies. If you succeed, right, then you can go for the next study. So that is nothing but your in vivo. In vivo means inside the body, not human body, right? It is related to the mouse or related to a rabbit. So what we are having, not here in Hyderabad. So the they are having the mouse modeling, right? With mouse they are going to do it. So this is in vivo. So we are going to do in vitro, means we are going to create environment similar to that of the human body, I mean in the laboratory, and we are doing the studies. That facility is there in our lab. We are trying to do that. So this is I mean the third step, right? And once you succeed, then it will go for the clinical trials, right? So I think you might have seen so many movies, right? So recent movies, there is a drug mafia is going to happen, right? So it is not that much. Even to get the permission for third step, right, we need to follow a lot of protocol, and you imagine about the clinical trials, right? So clinical trials is a very, very, I mean, difficult thing. I think it may not be possible throughout my lifetime. Okay, so that is the fourth step, and once you succeed in the clinical trials also, then your product will release right into the market. And but in I mean, if it is a general thing, it will try to take years together. But during COVID, right, you know about the vaccine, right? What is that vaccine? Bharat Biotech they have given, and one more, Covaxin, COVID, right? So because of the emergency, right, it took almost 6 months to 8 months, because the emergency, even for small, I mean, vaccination or medicine, right, it will try to take. So they will follow these protocols. This is must, right? So this is the, I mean, brief review of the steps which are involved. The material into product. So these are the steps which are involved as far as the biomaterial is concerned, right? So these are the some of the material. So we are doing for last several years, right? So Mr. Sushil Rajkumar and one more guy, they work in the glass and glass material, and one Srinath and the one more student, they work on the this crystalline material, right? So it's going on. So our journey is going on. But for us, the inspiration is Professor Hench, right? So that is the base composition, right? To start our work. So these are the material already I have given. So this gentleman has inspired us to work in this particular area. I think almost all 15 years back. I think if I remember right, Rajkumar se pehle. So almost all 10 to 12 years back, we have started to work this particular, I mean, area. So this is, I mean, triangle. So I'll try to show some of the results. I won't go in detail because for the completeness I am giving. But as far as our topic is concerned, we need to go more towards the biological aspect a little bit, and then the remaining more, right? So usually when you are working with this biomaterial, composition is important, right? Glass composition is important, right? So in the composition, we need to understand the role of each and everything. So here if you see the composition, right, we'll have the glass formats, B2O3, SiO2, they are the unconditional glass format, they'll try to form glass, and then basing upon the type of tissue, right, we are going to, I mean, use the dopant or additive, right? So we have chosen zirconium in this composition because of its mechanical properties, right? The fracture toughness, the yield strength, right? it is about 6 CGPA. That's why you are trying to GPA, I mean gigapascal. That's why I chosen this particular material, and it is a excellent compatible biocompatible material, right? So we'll try to weigh the material, individually try to grind it with the help of a motor and piston, right? After making a fine powder, we'll collect in a crucible, the platinum crucible. We'll keep it inside the furnace, we'll heat it, and then by melt quenching technique we are going to make it the glass. Basing upon our requirement, and the mold, there are different molds are available. We can make a pellet, you can make a rectangular shape, square shape or cylindrical shape, whatever I mean the size shape of the specimen required for the properties we are going to do. There are certain standards. If you want to do the mechanical properties, right, there are such standards, right? So accordingly we are going to make the sample. For example, if you want to measure the hardness, right, and then the mechanical strength, the other mechanical properties, there are certain dimensions. We need to prepare the sample accordingly. And you can make the pellet or you can make the powder for the in vitro, I mean measurements. So these are the characterization techniques you are going to use to confirm the bioactivity of the material, right? So these are the X-ray, XRD, Fourier transform, scanning electron microscope, EDS. Then for measuring the hardness, you are going to use the Vickers hardness test, right? So the after preparing the sample by melt quenching or by any the chemical route, right? We are going to test whether the material is active or not. So the first step which is involved is in vitro, outside the human body. I mentioned about SBF. This is a very fast, low cost first step to check whether the metal is active or not, right? So if you see that table, right, there is a comparison between the blood plasma and then SBF. That SBF is almost all resembles your blood plasma. So those are the constituents of the SBF, right? So what you are going to do here, we are going to, I mean, prepare the sample, make it a pellet, and then we are going to immerse the pellet into the SBF, stimulated body fluid, right? After 3 days or 7 days or 14 days or 24 days or 28 days, whatever the duration of time, we are going to remove the sample, we'll dry it, and then we are going to check it out. We are going to characterize. Before immersion, we are going to characterize. After immersion, we are going to characterize. So why I am talking about this here? So we are testing whether the material is active or not. So how you are going to confirm means by means of this particular study. So what is going to happen here? So in the beaker, you can see the material. So that is SBF, and there is a bioceramic, there is a pellet. So there is exchange of ions between your SBF and the material and then SBF. So there is a exchange of ions. You know about the nucleation and then the growth. What about it in material science? So there are certain nucleation centers around which the material will try to grow and it will try to spread throughout the, or you know about the crystal growth, right? So here there are certain nucleation center around which the material try to start growing during your 3 days, 4 days, 7 days, 14 days, 28 days, whatever may be the duration. So what happened? You are immersing your pellet into the SBF, right? So what happened? There is an exchange of ions, right? So as a result, there will be change of pH. There is a change of degradation. All these are the test to confirm whether the metal is active or not. So that's what you are doing here. So we are, checking whether the metal is active or not in terms of pH, in terms of degradation, or okay. This is about the biocompatibility, cytotoxicity, right? So this is a protocol we are going to follow to check whether the metal is toxic or not. So we are going to do in triplets. So this is 96 well plate. So each sample we are going to test in triplets, not a single, because we need to check, multiple times, right? So accuracy is important, right? So that's why we are going to do in triplets, right? And we are going to test with the different materials with different concentration. right? So to each material, we are going to feed around about 5,000 cells, right? And you are going to check by statistical analysis, you are going to check how much the viability of the cells, right? So this is regarding the toxicity here. Human astrosarcoma cell. So that is a bovine cell, human bovine cell. We are going to extract, and then those cells you are going to use to test whether the material is toxic or not. So this is the biology. I don't want to go in detail. So this is regarding the mechanical properties. So we are going to measure the hardness, the fracture toughness, the compressive strength, the elastic moduli. Not only this, we are going to do the aberration also, and similarly, we are going to do some the static analysis. Okay, so this is XRD for the amorphous material. So from this, you can confirm the material is class. It is amorphous in nature, right? Don't have any specific orientation, right? So this is confirmation whether the material is amorphous or not. Now yeah, so this is before immersing the sample. So we have prepared the material, we have characterized the material simply, right? So we confirm that the material is amorphous in nature, right? Then what you did, we immerse the sample in simulated body fluid, and we remove the sample after 5 days, and then we have characterized the sample. You can see the crystalline peaks, right, at 0, 0, 2, 211, 203. So these are the crystalline peaks. So this is related to the calcium phosphate, the hydroxyapatite. So what happened here? There is a leaching of ions between the metal and then SBF. So because of the leaching of ions, right, because of the nucleation centers and then the growth process, slowly as the time progresses, the layer has formed, and we are confirming by means of XRD. This is first step to confirm the material is active or not. Similarly, after 15 days, we recorded the XRD. You can see the intensity of the peaks, it is increased compared to the previous case. Right. Similarly with the FTR, this is before immersion. We recorded the FTIR, and we saw some functional groups which confirms the presence of the material what you have used. But after immersion, right, in simulated body fluid, and we are recorded after 5 days, we can see 560, 600, that peak is related to the hydroxyapatite. So we can confirm even from FTIR also that the layer has deposited on the surface of the material. Not only that, with SEM also we can able to confirm. See here, this is before immersion, this is 5 days of immersion. You can see the white precipitates on the surface. After 15 days, you can see the cloudy like structure. So that is the layer which has deposited on the surface of the material. So that is the hydroxyapatite layer which is deposited. So which is confirm the metal is active. And similarly, you have measured the mechanical properties also. So zirconium is about 600 to 620 range we are getting. I'm talking about the hardness. So which is very good as far as the mechanical properties are concerned. So the hardness is 600 is not a small thing, right? So we can able to use for the heart issues. That is the advantage of using. And this is to confirm whether the material is toxic or not. If you see, right, this bar graph, so Z0 is without zirconium, the base structure, the base material. Z1 is 1%, Z3 3%, Z5 is 5% of zirconium. And if you see the graphs, right, so all the bar graphs, right, they having the cell viability above 70% right? So the first one is the control, other four are with the different compositions, right? So all are slightly 80 and above 80. Second one is 70 and above 70. Third also 70 and above. Last one also 70 above. So as far as this particular bar graph is concerned, if you see here, we can observe that cell viability is above 70%. So as far as the standards are concerned, if the viability is above 70%, the metal is non-toxic in nature, right? So this is a cytocompatibility or cytotoxicity test we are going to do. Similarly, these are the optical images we are recorded. So you can see the flakes there. These flakes. These are live cells. The live cells, the bovine cells. We are going to feed the cells to the material. Those are the live cells. So we are having the 50 microgram per ml. Our material is 50 micrograms use, 2000 gram. So we can find the live cells, but there are little bit, we can see the dead cells also, but still it is above 70%, even 1000 micrograms or means 1 milligram. So it is not toxic. So this is regarding the optical image. This is different ways of confirming the metal is toxic or not. So similarly, we did with titanium also. So see here, still you can observe the titanium dope is more biocompatible with the glass material. See the crystalline peaks. You can see the functional group corresponding to 560 and 561, 609 related to the calcium phosphate. So these are the, so not only that, you will have the confocal microscope also. These also will try to distinguish between the live and then the dead shells, right? So there are different ways, and you can see, you can confirm whether the metal is proliferating. We help the tissue to grow. That is also there. Not only active, sometimes what happens, the metal try to help the tissue to grow, right? Which is nothing but the proliferation, right? So that also can able to confirm. We can able to see how the cell morphology is trying to affect with the material, because we are using our material. If it's toxic, what happened? The cell will try to die, right? If it is not toxic, right, this is live, we can able to see, and we can able to see the proliferation also by means of confocal microscope. So many are there. So this is Sushil's work. So he has done some drug delivery studies also. Oh, right. So I'll try to take half an hour, and then we'll go to the lab. So if any doubts, any queries regarding, you can ask. So the first topic, the first part what I discussed so far is related to amorphous material, the glass material. Similarly, you can able to use glass ceramics also, right? But the topic which I am going to discuss now, it is crystalline material, right? And here the material you can able to use for tissue engineering application, for light emitting application, right? The PASPAR application. We can use this material even for the supercapacitor application, like the energy storage devices, and then we can able to use this material even for the photocatalysis also. That's what our title, relevance of the title, right? So here we are not use the chemicals. As far as these studies are concerned, we didn't use chemicals. We concentrated more on the recycling waste, right? So we took the source, right? The rice husk, the eggshell, right? The peanut shell, the coconut hair, the baggage pitch. What I mean to say, we are use agriculture waste, we are use the food waste to start our work. Why you are use? Because these material, if you take rice husk, or if you take the peanut shell or coconut or the baggage piece, these are the major sources of silica. Silica, SiO2, not silicon, silica. And then we are use the eggshell, egg, the outer cover of egg. Snail also can able, the snail shell, you know, that is also we are use, and that is a source of calcium oxide, right? So our aim is to produce nano, crystalline material, right? So we took recycling waste material, we took the biomass material, and we have started, I think almost all 7 years back, 7-8 years back, I started to work in this material. And why I use this material? Because the material are bioactive in nature, biocompatible, degrade, stability, they have the good mechanical properties. So there should be some reason behind selection of the material, right? So this is one area, and similarly we have chosen the industrial waste like fly ash, which is also the major source of silica. We have used GGBS, the granulated blast slag, which you are going to get from iron and then the iron ore industry. So these are the sources of silica and then calcium. So Pooja and then Gangadhar and then where is Swarup? So they are working on this combination of the material, but respective applications, right? Some of them they are working in energy storage application. Pooja, Gangadhar is working for multi-functional application. Even Swarup also is concentrating more on the biological aspect, right? So here, we have started with something. We are working in something. It's, it depends at that particular day what is your requirement, right? So even it depends upon how your research scholars will try to work, right? So it depends upon the ideas, right, which they are going to get, and then how effectively you are going to do your literature. That is also very, very important, right? So it's combination of, I can say, the permutation combination, what it may be. So our aim is to use these biomass, the recycling waste, waste to wealth. That is our motto, right? So these sources we are used, and then we have yeah. So this is our interest. If you see here, you can find major, the calcium silicate constant, right? So these are calcium silicate based ceramic material, nanocomposite, nanomaterial, right? So you can see wollastonite, calcium silicate to hadrostenite, malolite. All these are the material you can able to grow by means of using those recycling waste. Combination of agriculture waste, food waste, then industrial waste. With the help of them, we can able to, cover all these, structures. So those structures, they are having the multifunctional applications. So the beauty of those structures, they are having the perovskite structures. We can able to develop the sensors. We can develop the biomaterials. We can develop the energy storage devices. So many applications are there. That's why we're interested towards those material, right? So if you see here, as I mentioned, rice husk is the major source of silica, right? It contains almost 99% of silica, right? And then eggshell, it contains the calcium carbonate, right? If you heat it, make it powder, and if you heat it, what happens? It dissociates into calcium oxide plus carbon dioxide. So carbon dioxide will try to evaporate, will try to get CO. And then basing upon the selection of this material, 1:1, 1:2, or 1:3, we will try to get calcium silicate, dicalcium silicate, and tricalcium silicate, right? So selection is also very, very important. So this is the technique, I mean, we are use to make calcium silicate by means of using the soil gel method. So we got the Indian patent for this particular method what we propose. So here these are the steps which are involved, right? So our students will try to, I mean, give the demo for this particular method, the soil gel method, and then the hydrothermal method, preparing the calcium silicate or acarmonate structure, whatever structure is to call, right? So here this is the method, I mean, they are used to I mean follow to prepare calcium silicate or zirconium doped calcium silicate, right? So we can get in terms of pellets, powder, or whatever shape we want, can able to get it. And then we have recorded the TGTTA for this sample, and from TGTTA we can confirm that the TC, the crystalline temperature of this sample, is around 778. So what we did, we have fixed the crystalline temperature of 800, then we anneal it. You know about anneal it, right? Annealing, you know, right? Quenching and annealing. Quenching means fast heating and then fast cooling. Anneal means with a prerequisite rate, you are going to slowly heat it and then slowly cool it. If you follow the quenching, what happened? It won't find sufficient time to find the brevis, lattice, or lattice sides to give a structure. Whereas if you follow the annealing, what happened? It finds sufficient time, right? So it results into crystal. Quenching results into glass amorphous material, right? So basing upon T and T, temperature and time, right? So you will try to get the phase transformation from glass or what it may be, right? So we, I mean, optimize the temperature and then we anneal it for 2 hours, 3 hours, 4 hours. So time you optimize, temperature optimize, and as a result, we got the structure. So this is the XRD, right? Without immersion. Remember, the previous one is glass. We got the amorphous structure, but now it's a crystalline. It is having some structure. So we compare with the JCPDS data, it index, right, with that number, and the structure is beta wollastonite. So we are having different structure, anarthrite, wollastonite. I'm talking about the calcium, even in calcium silicate also, right? So this is the structure of the calcium silicate what you have prepared, and then we want to check whether the material is active or not. So what you did, we immerse once again in the SBF for 3 days, 7 days, 14 days, 21 days, 28 days, right? Then you have recorded the spectra. We recorded your XRD, right? So we can see a peak at 25 degrees, we can see peak at 31 degrees, right? So all those peaks are corresponding to hydroxyapatite, which means that the metal is active, which is trying to, I mean, interacting with the tissue, right? I mean, I can say the SBF, right? We're depositing a layer, right? So those peaks, right, corresponding to the hydroxyapatite. And see here, this is the SCM. So the first one 0 days means without immersion. We prepared the sample, we recorded the SCM, we have the morphology. And after 3 days, 7 days, 14 days, we can see a precipitate which is forming because of the exchange of ions between the pellet and then SBF. You can see the thickness of the layer here. This is SBF layer thickness. This is a material, your pellet, and this is as the time grows, I mean, 10 days, what happened? The layer is trying, thickness of layer is trying to increase. So the cross-sectional I am trying to showing here. So it is the layer which is deposited on the surface of the material, right? Suppose this is the material, right? So you are immersing this material into the SBF. So because of the exchange of ions, right? So they will try to find the nucleation center around which the material try to grow, right? So the layer has deposited. This is a microgram, the cross-sectional view after soaking 3 and 7 days. So it is increasing from 49 micrometer to 120, 140, 150 micrometer. I am talking about thickness of layer. Means the metal is bioactive nature. So activity is more here, and you can see the EDS, right? The elemental analysis, right? You can see the EDS. So you can see their Ca to P ratio, right? Calcium to phosphate ratio, right? After immersion. So what is happening there? It is increasing 1.24, 1.56, 1.63, 2.2. If you take the bone, right? So if you calculate the calcium to phosphate ratio of bone, it will be about 1.66. So you can see here it is almost all same as that of your bone. So that's why we can able to use this metal as a bone replacement. So similarly, you can confirm by means of FTIR. You can confirm the activity by activity even with pH also. See what is happening. So we are preparing the SBF at 7.4, but what is happening? It is increasing. So there is a change in the pH of SBF because of the material. Even degradation, the weight loss also can able to calculate. So why weight is lossing? Because of the activity. So the same thing we are trying to confirm in different ways. Getting my point or not? Our aim is to check whether the metal is active or not. To confirm that, we are doing XRD, FTR, FPSCM, pH, degradation, and so many things you are doing. So these are different ways of confirming. And then if you see this, so here the x-axis is the concentration of the material you are trying to use to check the toxicity of the material. 50 microgram to 1000 microgram per ml. Even you are used for 2000, 5000, even more than that also I use. Still we are finding that our metal is non-toxic in nature. See, the viability is near to 100%. So similarly, I measured the mechanical properties also, like the hardness and then the compressive strength. So similarly, we are doped with silver also. So silver we are using because it is having good antimicrobial properties. That's why we are trying to dope the silver also to calcium silicate. So this is the procedure you have followed, the soldier technique you followed to prepare the silver doped velastronite. So this is the XRD analysis, and you can see the growth of layer on the surface of the sample, right? You can see the different morphologies. So all these the recorded images with SCM to confirm whether the material is active or not. So on the surface of the material, the layer will try to grow. The hydroxyapatite layer will try to grow, and you can see with the time it is trying to change. So it is having different morphologies, flake-like structure, globe-like structure. Then you know about the cauliflower type of structures. So we can try to see different morphologies as the. So what actually is happening here? There is a leaching of ions between your material and then the SBF, right? So because of that, there will be nucleation centers around which the material try to grow, and with the time it will try to expand throughout the surface, and then the thickness of the layer also increasing, and it is spreading throughout the surface, which already shown in the previous image. So similarly, you can confirm by means of a variation in the pH value, weight loss also. And this is the important test people are used to perform to check whether the material is allergic or not. So we are going to do the antimicrobial study, right? And they are done only with two species. One is E. coli and then SRS. Not only these two, we are having 60 to 64 species are there. It depends, right? Sometimes you know about the skin allergies, right? Before going to use any ointment, you are going to check it here whether it's allergic or not. So it is allergic to which species, that is also very important. So basing upon the availability, right, we are done with E. coli and then SRS, and you can see it is you can see the images at the top, right? So it is the inhibition zone, right? So with the silver content, so the diameter of the inhibition zone is increasing, so which confirms that the material is antimicrobial. This is also one type of study you are going to do it. So that is regarding in vitro cytocompatibility, right? And after this, I already mentioned about the in vivo studies inside the rabbit or mouse modeling, right? And then the clinical trials, and followed by the product release into the market, right? So it is not that much simple as I mentioned, right? Up to the second stage, a part of third stage, which I mentioned in the slide, is possible, right? But the animal modeling, like rabbit modeling or the mouse modeling, is a very difficult procedure, right? As I already mentioned in the beginning, I am trying for last 11 years, right? But I didn't succeed because we need to spend, money is also important. For testing one material, we need to spend 1.5 lakh rupees. And even if you spend it, we don't have a guarantee that we will get the results, because maintenance of the environment, because the mouse is maybe 2 weeks, 3 weeks, 4 weeks. So we need to cut the part. If you want to use as a bone implant, you need to cut the bone. Which part of the bone, or whether at the joint, or at the skull part, or at the finger part. So we need to check it out. So for that, we need to take the permission from the animal husbandry department, and then we need to consult with the orthopedician doctor, right? So after testing the material, right, we need to record the X-ray, right? Not this XRD which I am talking about, X-ray, right? So that X-ray is I have shown. So that X-ray is very, very important. So during this course of the test, the mouse may die. That is also very, very difficult, because we tried, but we didn't get the results. That is also a typical, procedure which is which required to take a lot of permissions. So once you succeed, then it will go to clinical trials, and then the last one, the product will try to release into the market. So this is regarding the first part, and in the next session, I will try to explain about this thing. So what we are doing now, and which is related to our Gian course, right? So I will try to explain on the energy storage application, the optoelectronic application, and then finally I will try to show some light on the photocatalysis also, right? That in the next class. So we'll have a break now. After the break, I request to proceed to physics department, right? So there, our scholar will try to give the demo about those two methods. If time permits, today we will try to show you FECM. Otherwise, we'll try to show you tomorrow or day after tomorrow, right? Because it is already 3:45, I think. Okay. So if any doubt, you can ask me, or you can discuss right during tea time. Okay. Inhibition, yeah. It won't. Yes. Otherwise, it is a measure of allergy. That microbe it won't enter. That is because of the material. The material is inhibiting those particular microorganisms. SBF. Which one?
Yeah, you know the mechanism related to the crystal. Okay? If you want to provide a crystal, right, it should be some relation. So it is helping to grow the crystal first. That is the second thing is related to when you immerse the material into the stimulus body fluids, but there will be a change of sound. It requires some inflation. So silica or some other inflations. Around which it's 100% of the material. But we need to buy. And after the demo, so the tomorrow session also start on today. We are going to discuss about mainly the first one, solving hydrogen. So to a maximum extent, we are trying to show 1 meter maximum second meters. So because we like to take at least half an hour, 1 hour, even more than that. Right. So in the first part, we like to finish the experimental technique, how to synthesize the nanomaterials by soldier and then the hydrogen. So tomorrow in class, right after your session in the seminar hall, you directly come here. So we are going to show you how to make a device. Means the supercapacitor, how to make the battery, the storage battery. We will try to show you, and then we will try to give you demonstration of that particular battery, what we are going to fabricate with our material to blow the electronic gadget like the LED or calculator or some sort of electronic gadget we are going to grow by means of the material which are grown by means of soil method, right? So today I will try to demonstrate various steps which are involved in preparing the material, right? So tomorrow by using that material we are going to fabricate the device, and means battery you are going to cell, you are going to supercapacitor cell, you are going to fabricate it, and then 2 cell or 3 devices you are going to use it and blow the electronic. That is the first. And second one, we are going to give demonstration for the hydrothermal method, and the same material we are going to use to give a demonstration how we are going to what you call use for the wastewater treatment. By means of photocatalysis technique, we are going to eliminate the dye. So we are going to explain to you the procedure to eliminate the dye from the industrial waste. So we are going to use our material, right? With the help of the material, we are going to remove the dye which is present. Right. So we try to explain to you the methodology, characterization, and application, right? Which is mostly relevant to our title of the program, right? Photocatalysis and history, right? So calculation part, Mr. Sushil will like to explain, right? And then the synthesis part, theory part, she will like to explain, and the experimental part will explain both by Gangadhar as well as so, right? So it involves calculation. See, when you are preparing any material, whether it may be glass, ceramic, or nanomaterial, so we need to do some calculation, right? I mean, suppose you are preparing for 1 gram, or 2 gram, 5 gram, 10 gram, whatever the quantity. You need to know what are the precursors you are going to use, what are the solids you are going to use, what is the pH value. So how much the yield we require, right? And what are the precursors? See, if you are using precursor, which chemical you are going to use? But you are not using chemical, you are using some sort of industrial based material to prepare our material for the application, right? So first part we'll try to explain by Sushi. We'll try to tell you the calculation part, right? So you try to note down all the calculation part, and then once you understand the calculation, which I will try to explain about the theory, what is happening, right? So in soldier, what is how the solution will like how the solution will get to form, and then you need to dry it by means of using the oven. Then you need to centrifuge it. Then you need to centrate. And how you are going to centrate? You know, I given the temperature optimization, which are going to get by means of ECDT. So how you are going to centrate? We have in the ovens. We have in the furnaces. 1400 furnace is there. The 600 furnace is there. So that also we will try to show you. So she will try to tell you the theory, what is happening, and Gangadhar and then Saraswati will try to explain the experiment part. Right? So today we try to learn and you just try to work out for a composition. If you have any difficulty, you can ask them tomorrow. But tomorrow is exclusively application. We will explain about the device, the cell, and we will explain about the photocatalytic. Technique like this. Is it okay? Over to you.
Actually, there are lot of synthesis techniques. There are physical method, chemical method. So usually for the synthesis of nanomaterial, physical methods are there and chemical methods are there. So physical methods are those methods in which the chemical reaction is not involved. So like ball milling or solid state reaction method. Or laser ablation methods. So like that, these are the physical methods in that no chemical reaction is involved. It's physical. So second one is chemical method. Soldier method of synthesis, hydrothermal, solvothermal. Co-precipitation method. Emulsion method. There are a lot of methods in so all these chemical process, chemical reactions are used. Are come under the category of chemical process. So today we discuss about soldier method of synthesis. Later on we discuss about the hydrothermal method. So in soldier method of synthesis, basically 5 steps are involved. So first one is hydrolysis, then polycondensation, and then aging, then drying, and then calcination. Basically, 5 steps are involved. First one is hydrolysis. Second one is polycondensation. Third one is aging. Fourth one is drying. And fifth one is calcination. So we'll reaction of metal alkoxide with the water. So it will form metal hydroxide plus water. Okay. So this reaction is known. Second one is polycondensation reaction. So in that these metal hydroxide that will form a 3D network, cross interlinking of this metal oxides. And they will form metal oxygen metal bond. And there is a release of water or any alcohol compound. So removal of that and they are forming the metal oxide. During this step, during that time, polycondensation time, gelation takes place, gel kind of formation. You will see during the demonstration time, they will show you the gel kind of things, viscous So at first in the name itself, it is a soldier method of synthesis. So sol is actually, it is a colloidal suspension of solid particle in liquids. And the gel, we are talking about gel. So gel is a 3D cloth interlinking of these particles surrounded by a liquid. Means in that there is a more solid particle. Means we can call it as liquid in solid. Solidification of gel. If the viscosity of the gel network will be formed, so that viscosity is increasing. In case after that we'll put in a dry, we'll dry it in a hot air oven. So and then further we do the test for the calcination in a muffle furnace. So as sir mentioned, at first we have to do the PVDT of the dried sample to know the crystallization temperature of the material. So basically, actually, as I mentioned in the hydrolysis, we can take water. If we take water as a solvent, so we can call it as aqueous solvent process. If we take other alcohol material, then we can call this process will change accordingly. The name of the process will change accordingly. And what amount of water is required for the solution, that will also decide the viscosity of the gel, also that interlinking of the metal oxides. So this is a theory of this process, and my senior will tell the calculation, the molar mass calculation of this.
Okay, so you have noted what are the steps? Very many steps. You have noted? Relationship. So relationship is A assigned. Okay, so it has two components, relation oxide and assigned. Okay. So by composition, they have equal mass ratio or molar intensity. So they both, when they are both in 50-50%, then they will form a rising state. So what sir had told is, I have told you that about beta velocity and something like that current produces during the presentation. So that is only calcium silicate. Because calcium silicate has different form, but one of the forms beta velocity. So we are going to prepare this this form of calcium silicate. Okay. So for making this, we need in what percentage we put. So in nature they are in 50%. So we will take both in equal mole percent. So these are 1:1 molar ratio. Unity. This is in molar ratio. Okay, that is the important point, that they are in molar ratio, not weight ratio. If they are in weight ratio, what we will do? We will take 1 gram of calcium, 1 gram of silicon also, and then rapidly we will dissolve and rapidly mix it and get the calcium silicate. but they are not by weight ratio, but they are by molar. Okay. So for preparing 1 gram of calcium silicate, we will multiply this by their molecular weight. Okay, so molecular weight of calcium oxide is 56.0, okay, and the molecular weight of SiO2 is 60.0. Okay, so we divide one by another. You can divide it by SiO2 or divide it by Ca. So I divided by molecular weight of Ca. Okay. So for 1 gram, what will be the value of 1 stream? What will be the value of this SiO2 ratio? For preparing 1 gram of calcium silicate, you need 1 gram of calcium oxide and 1.075 gram of SiO2. Okay. Okay, understood? That much you understood? Okay, next. Now, for performing a solid method, what you need to do? You need salt. Okay. So you first have to prepare the salt. Okay. So for preparing the salt, you need a solution. Okay. So what we will do, one of the basic property of SiO2 in amorphous form, it will dissolve in NaOH in highly basic condition. In highly basic condition, it will dissolve. In normal condition, it won't dissolve. Highly basic. So what we will do, we have to dissolve SiO2 with NaOH. That will give us sodium 3. Okay. Okay. Now this is the reaction. The reaction, what we have to do, it should be equivalent oxygen. Plus water will also get reached. Okay. So here we have two sodiums. We have to multiply it by 2. Now this equation is correct. Okay. Okay. So now we have silicon oxide, but we don't know how much NaOH we want to dissolve. If there's some exact amount using this, we can dissolve this. Okay. And we don't know how much calcium sodium silicate will be. But what we know the molecular weights. What is the molecular weight of NaOH? 39.9. And is there something molecular weight? We just need one valence chemical bonds. Okay, so now we need one thing, we need 3 things, and we need 1. Okay, so from here we can calculate extra. What will the value become? Calculate. One 1.075 multiplied by 2 into 40 divided by 60. One point 4 to 3 gram. Okay. So this is in gram. Okay. But our solution is present in liquid form. Okay. This is not liquid, this is solid. We need liquid. Okay. So what you can do, one thing is that you can divide it by density. Okay. Or another way is we can calculate the number of moles or mass of molecular mass. Tell me what will the value now? You know, moles, you know, what is moles? Because we need to prepare 2 molar NaOH. In this solution, we will dissolve SiO2. So we got the value of NaOH, which is solid form. This we need liquid. So we will dissolve it in water, but if you do that solution will have some strength. Okay. So that strength is 2 molar. M is for strength of the solution, molarity. So calculate what will be the number of moles of what will be the number of moles of NaOH. Divide 1.431 divided by the molecular mass of NaOH. I think it's 0.03 Kelvin. Now, what is molarity? Molarity is number of moles divided by volume, which is between liters. This volume is generally volume of the solution we need. So we know the moles, we know the molarity, we can calculate the volume of the cell. Volume of the NaOH is from 0.035 divided by number 0.0179. That is in liters. We converted into milliliters, so 17.5 ml. Okay. So from this, what we got? That to dissolve 1.075 SiO2, we need 2 molar solution of NaOH. So this will be our solution A. Solution A is sodium solution. Here noted molecular weight of the resin. this value of x you will get 1.30. Okay, now we'll calculate the direct value. So it will be 1.301 divided by x. What will be the value of x? Zero point 0.78 liters. So they got 17.8 ml of 2 molar HCl. 2 molar HCl to dissolve in everything. That is our solution. So this reaction, the first one elevated temperature starting with 70 degrees, we can increase the temperature. Then also this reaction will. This reaction will happen at room temperature. You don't need any temperature, it will happen at room temperature. After preparing these two solutions, we add solution A dropwise in solution 2 until we start to form a C. Now it will be demonstrated by Gangadhar.
Means
Then it will be understood.
honey from
See
Right,
here,
yes, yes.
one important thing that here they have used similar HCl. It is not mixed. Okay. That is the strength of the solution. Here for our material, it was at 2 molar solution. You can change this strength to 3 molar, 4 molar, depending upon your material. This you will find from experiment. Then you will, because with this comes the value of pH. It is not because we are taking 2 molar animals, that's why our gel is forming. It is because it is using this solution we are getting that means at least the soul will gel will come. Sometimes it can happen that sometimes we take direct concentrated HCl, like from the bottle 36%. It is pure HCl that we get. We take that as that way also this sometimes we don't get the gel. So it is not a fixed formula. We got the gel at millimolar of HCl also, millimolar of HCl. We can change the concentration of the solution, strength of the solution according to the solution. Because that will affect that the concentration, that the strength of the solution will also affect your final crystal size will also be duplicated. you can get, maybe it may happen that your morphology of the sample will change. So this can also happen. So depending on the case, so many components.
Increase and decrease the strength with speed of the reaction. If you take the higher strength solution, then your reaction will speed up. And these are the calcium oxide and silica SiO2 we extracted from the eggshell enterprises.
See, this size was we have collected from the nearby factory. Okay, this size was we have collected from the nearby factory, and we have treated this with 1 molar HCl solution at 70 degrees. The previous researchers have shown that at 70 degrees we can get maximum silica out of ices. So we have used those conditions to extract SiO2. Okay, we treat it and HCl, and then we'll dry it in oven. Then we'll do calcination at 700 degrees Celsius for 5 hours. So it will turn into this white powder. Similarly, for Excel, you have all written X at home. Okay, X you have written at home. You are vegetarian. Okay, you have seen in TV that while they break the egg, inside some organic film is there. Okay, so what we'll take the eggshells, we'll remove those organic films. Okay, then we'll wash it, and then we'll grind in pestle and mortar to a fine powder. Then we again we do calcination at 900 degrees Celsius. So we get this beautiful white powder. Okay, that we can use for our.
So there are other sources also you can use, like you sir mentioned, Schnell cell is also a source of calcium oxide. But majorly in the eggshell there is a higher yield of calcium oxide we are getting. That is why we are using. You can use other sources also. As for the silica also, other sources.
Other sources like you can use peanut shells, you can use
Sugarcane husk
you can bus, but
husk also you can use.
okay, then coconut shell you can use. Okay, all those things contain silica, but the percentage of silica is very less in those. They around 50% or 60% or 30%, because they have mixture of some other oxides will be there. Some like peanut shell will contain 35 or 50% of silica, plus they have sodium oxide, potassium oxide. So generally, we try to use the material according to our use. Like if we want potassium in our final product, then it is better to use peanut shell. Okay, like if you want a mixture of the things that contain iron, like industrial waste, which is working with fly ash. Fly ash has good percentage of iron. So in your final material, if you want some iron percentage, then you can use fly ash. So according to your application, you have to change the waste material.
Actually, one of the major advantages why we are using this waste material, not only the final product we are getting that calcium oxide, CFI. When it is both the solution A and solution B, so it will assign with the CaCl2. So that final product will give you CaSiO2 plus 2 mother of NaCl. So not only that you will get in the final product, then you use this waste material, except from this you can get other transition metal oxides also. Because as if you take the industrial waste material, as I'm using fly ash and BCA. So apart from the calcium and silica source, they are having iron also, potassium also, or magnesium also, or titanium also. So that will influence the optical property. So without any external doping, we can enhance the optical property of the material. So this is one of the major advantage of using the waste material. We can exploring other waste material like sir mentioned that industrial waste like nowadays people are using marble or granite waste. So marble, they reported that it is a source of calcium oxide and granite is a source of silica oxide. So you can exploring that area also.
We'll continue. Another is means wollastonite, beta wollastonite by Solgel method. So we are taking two precursors. One is Ricer's glass that is derived from the Ricer, and another one is egg cells. As my fellow scholars, they have told how to derive these egg cells and Ricer's glass from the agricultural waste. So first, so all the calculations they have already told you how to do the calculations. So we need how much? So 2 ml of 2 molar of HCl, 17.6 ml to dissolve 1 gram of calcium oxide. Similarly, how much? 17.5 ml of NaOH to dissolve 1 gram of SaO. So we have already prepared 2 molar of HCl and 2 molar of NaOH. So from this we'll take 17. Okay, we'll take 17.5 and 17.6. First time taking 10 ml. That bit we have already used for this. And we have heated it at 80 degree will be. Okay, at 90 degree we are heating because it needs some temperature to dissolve SaO2. Okay, at room temperature it won't dissolve. Okay. Then we'll take 2 molar of HCl. So there will form one solution, here will form another solution. So how much? This one I will clean. 50 water. Cleaning is important. So because if it will be any impurity, then reaction won't happen. But your product will be a different product. You don't do whatever you want. This is 10 ml. I'm taking. How much? SC is needed? 1.2. No, not 1.2. Here below. 10 will find 8. 7.2. Using the same way. We'll stop that one also. So now we'll measure the figures. Too much hard. Because it's that will make this 0. Okay. So it should be exactly 1. Because positivity is equal. Why we have turned on off the fan? Because this is high sensitivity. So to measure the gold, we used to use this actually. Means it is maybe more than that. So 1 gram we have taken. So we'll dissolve it. Here it is. Slowly we'll dissolve.
It is a bit slow for the water. Or else you just feel this. That's give me. First we were a pencil. अभी this one was HCL ना? The result was actually. तो सिर्फ मैं बोल रहा हूँ.
HCl calcium.
Slow.
Maybe NaOH we are adding silica slowly.
पानी पानी डाल दिए
So actually we otherwise it won't be. That we don't. Now why we are doing this much calculation. Exact amount. So maybe they turn into
सब डाल उसको डाल के टेम्परेचर थोड़ा ज्यादा करो टेम्परेचर इंक्रीज करो 90 15 minutes to get 2 molar SC electric. Why it was not diesel thing? Because the problem was so it was prepared 1 molar SC electric. More solution. So there was a calculation error actually. Okay. इसमें गिरेगा पेपर से उसको निकाल तो सुनील भाई it's running एक भी नहीं है so we have dissolved 1 gram rice in 2 molar 16.6 2 molar NaOH solutions and 1 gram calcium oxide in 2 molar HCl solutions. So now we let it steep for 1 hour. After that, let us steep for 1 hour. Or let's continue. Okay. Yes, 15 to 20 minutes. After that, we are suddenly don't come for a 15 minutes. So we are using this wholesale filter paper. Let us filter this solution. So while we are filtering if any unreacted impurity is there, we'll take it out. We'll take only the dissolved silica solutions, Na2SiO3, sodium silicate solutions will take. So both the solutions, I'm just filtering. As you can see, the color of the solution is changing from transparent to milky. You can see. White is liquid is because of the formation of stool actually. Forming stool. Yes. We mix all the liquid drop white. Now we will stir it for 1 hour for completion of both reactions. Stirring completed, so we'll keep our stirring completed, so we'll keep it for aging. We'll tightly pack it, then we'll keep it for aging. We'll see tomorrow how the gel is forming, or after 3 days we'll see.